Welcome to my tutorial on SAT solving. So this is part of a boot camp of Berkeley Institute seminar on the theory and practical aspects of SAT solving. And originally this was planned as a kind of live physical event at the Berkeley Institute in California, but then through these due to this Corona and COVID thing, we had to move everything online. And therefore, I decided to do this a little bit differently than it was originally planned to happen. So originally there was like a plan for 1 day tutorials on particularly important subjects, like to get people going. But it's not possible, and so we're doing videos now. And so I thought, like, these videos, you can find them on the internet. Actually, you find lots of them, even from me, on talking about SAT solving. Just one recent one at the Saturn SMT Indian Winter School, so I recommend that one. And there are slides, and so I try to do this a little bit differently. So today we're going to do something which I call Blackboard. Okay, that's what we have here. It's a blackboard, but I'm also doing C, and C means code. And you'll see that in a minute. So what we're going to do is to actually while we're talking about like the basics and the algorithms, I'm going to show you how this really works in practice, and therefore I recommend that while you try to follow this video, or maybe just stop it now, go to the web and download this repository. This is a SAT solver I hacked particularly from scratch for this event here. The reason being, I have done something similar for a tutorial I gave in 2012. Back then it was called cleaning, and I just wanted to redo this thing properly now with new insights and simplified also in certain ways. All right, I hope you had a chance to download it. Then let's see, what do we have here? First of all, SAT rhymes on scratch. So there's a C and an R missing, but it's actually in C. So if you see these files, and maybe I'll explain maybe first things to find your way around, and then we'll talk about algorithms. So first of all, there's a README which explains things. So it's like a SAT solver written from scratch, and it's meant to be simple code base, so it's way simpler than my other solvers, KISAT and Cadical, and which have been really successful in the last two competitions. And you want to use them for production maybe. But this is much more instructive and much smaller. So you see here, for instance, that it really only consists of these code here, and like one file in which everything of the solver is. That's here. This one. Then there is like a stack, the only container actually needed, then a configuration, very small one for like keeping the build information around, and then at the end here, this line which says okay, it's an application code. You need a parser, actually, I think robust parser and a witness printer. Then there's the build system. In version, you find the version, and maybe we'll look at this for a second. So the version I'm talking about here in this video is version 0.2.4, and then we have make files, and yeah, I'll talk about these things maybe later a little bit. And so you can compile the whole thing as we just saw by just issuing configured. So this will generate a make file. We can say make, and then the solver is built. Yeah, and then we can also do run some CNFs, solves them, and then at the end also tries a little bit of API testing, even though this is not complete for this solver yet. Okay, so you should try this, and maybe also try maybe like one of these test cases, because this will print some nice output. So this is the output, so reading, then yeah, it starts solving. So I'm going to explain these things later, and then at the end there's the result. It's unsatisfiable. This S here is from the SAT competition output format, in case you haven't seen that. So like this is sort of the most important line in this file. If you, for instance, would here just write q for minus q, then we only get this file, this line with unsatisfiable, then some profiling information, and then some statistics, and at the end memory and time usage. Then the solver exits, and this exit code here is really the exit code. So if we ask the shell what was the exit code, it was 20. That's also like a common format from the SAT competition, where we had like 10 for satisfiable formula and 20 for unsatisfiable formulas. And of course the same would work for satisfiable, which factors these numbers, and therefore it's because it's a square of two prime numbers, it's satisfiable. And if I do that, then you get here exit code 1, but more important, you get here these numbers, like first of all, again, like a solution line, but now it says satisfiable instead of unsatisfiable. And then the solution here is printed as so-called witnesses line, or V lines, value lines, where sort of you write the variable positively or negatively. So you might wonder, why do these variables not have name? Well, that's the Dimex format, and maybe that's the next thing I show for a second. So if you look at this instance, you see here, this is a typical SAT instance with this is like a prefix, and that's called that. It's a CNF. And then here you have the number of variables occurring in these files, and this is the number of clauses. So if you go down here, you see like it's like this many lines and bytes, and right. And furthermore, these are the actual clauses, and CNFs are like that. But before I explain more about it, so you just need to think of this as, well, it would be as if you would have, maybe I pick this one with mixed, so this would be the same as writing sort of not x25 or x24, right? Then you have a symbolic representation, and then comes the next clause, and this clause would be x8 or not x24 or x25, and so on, and these are all connected with ands and so on. All right, so this is kind of, and this is kind of our task. How do you build a tool which solves such instances? So let's talk about the input format of a SAT solver. So it's a conjunctive normal form, and you must have seen this before. So let me just like make an example. So we have two variables, M and S, and obviously in these COVID times we'll have a shirt like my t-shirt I'm wearing here, and we also have a mask, and of course we'll just talk about now like conditions on these on these variables. So let's assume if I have a shirt, then I have to wear a mask. If I wear a mask, I should wear a shirt. That would be really strange, right? And then like one of the two should be true. So this would be like three constraints, and because they're in CNF, we're put an and together. Now these implications here, they're a little bit strange. So let's just transform them into a real CNF, and that would be there was an and that would be like replacing the implication by disjunction, and then we'll get these three clauses, right? And that's like our CNF. Now in this form it's already like less readable than here in the middle, and but it's I argue it's pretty natural to think in terms of such constraints for certain things. But let's not stop here. So let's just now simply say that like the shirt here is we have a number one. So once again, right, so we discussed this before, we interpret this as x1 and this here is x2, and then we have the Dimex format simply as right, so like not shirt, which means -1 or 2, right, and then 0 for terminating the clause, and then the opposite, so 2 implies 1, and the end one of them is true. Okay, you see that, of course, like I'm used to reading this Dimex format just literally very fast, but it's also pretty simple. So you have two variables and three clauses, and you could give this to a SAT solver. Okay, now the question is this thing satisfiable? And well, it is. Why? Because if you think about it, you're then one of these clauses here. So sorry, these three clauses are all the clauses which exists with two variables, except for one clause, right? So the clause which is not here is not S or not M, right? And so that would say I should not neither wear a mask. I should not wear a mask and a shirt at the same time, right? It's a negation of not S and M. And these four clauses would be unsatisfiable. Why? Because you have four assignments to these two variables, and each of them would be blocked by one of these clauses. And so blocking all of them would just make the formula unsatisfiable, but because it's satisfiable, we're going to have a satisfying assignment, which is exactly the opposite of the clause which is missing. Which is S and M. So you can think of S is true and M is true, satisfies these three clauses. Why? Well, you also see that yeah, this is true here, right? And this here is false. You can also think of the other way. So I'm making all variables true, and each clause contains one true variable. So that's why it's satisfiable. Okay, so this concludes my introduction into CNF. All right, now let's see whether we can also do this example with the SAT solver. So for that, we'll just start a new file, which we call sm.cnf, and then put in this, like our two variables and three clauses. Remember, the first implication was 1 implies 2, second one 2 implies 1, and the third one of them is true. Now we can solve it when we get like yeah, it's satisfiable. Remember this code here, but we'll also get this satisfying assignment, namely that the shirt here is true, and also the mask is true. Okay, so this is how satisfiable instances work. Now if I would do the same with an unsatisfiable instances. Remember, the sun became unsatisfied. If I add this clause, I need to make it 4 clauses now, and then the whole thing becomes unsatisfiable as expected. All right, what we're now going to do is trying to get a bigger problem into CNF, and we're going to do what people call the Zeting encoding or transformation, right? And for this example, I use my favorite sort of like well, there's some more, but this is one of my favorites. So we are going to use the distributivity law from Boolean algebra, which looks like this, right? So you get A or B, and then you can replace this by A or C. All right, and so let's keep this example. Now what we're going to do is to introduce variables for these individual nodes here, like I mean operators, and this is better seen in circuit format, and it has the additional advantage that the circuit you can apply the Zeting transformation to the circuit as well. So let's look at this left one. We have an A here, and then we have a B and the C, and the B and the C are go into an AND gate, which then goes into an OR gate, which has A as first one, and then this conjunction is second one, and this is our output. Okay, and then we want to know that this is the same, and I'll talk about this in a second, as the one on the right, and for that we're going to use an XOR. This is an AND or XOR, and I'll say more about this in a minute. And the output we're going to denote by O. Okay, and then of course you see that the top one here is an AND gate, right? And this AND gate has two OR gates as input, and all right, and they have the common B, the common A here as this is used in both, but then the right one has a C and the left one a B, modulo like commutativity of these gates, right? And in principle, right, what you really want to do is kind of get here this B, and also here instead of this A you want to get this B, but I'll just assume that they're really the same inputs here for readability. And now the question is, how do we get this into to a CNF? And basically what we're going to do is we're going to put new variables and mark them with blue for each of these gates. So if we have, like for instance, have here X variable for this OR gate, here Y variable for this Y gate, here Z for this AND gate, and maybe here U and V for these guys, okay? And then we simply write down like what these compute, and let's do this here. So let's start from the left. So from the left we have U is equal to A and V, okay? And then we do it for the other gates. So we have V is equal to B and C, so this is an input gate, and so on. So Z is equal to X and Y, and X is equal to B or A, and finally Y is equal to A and or C, okay? Right, now this is obviously a linear algorithm, right? But it's still not a CNF. So how do we get now from this to the CNF? Well, we need to translate each of these individual clauses here into CNF, and for that, let's maybe look at this clause here, right? So we're having u is equal to a and v, and you can think of this constraint as u implies a, and u implies v, and then both of them, a and v, imply u, right? Okay, now maybe at the end, so we're going to turn this now into a real CNF, but I guess you can see this already. So it's new a, and because I'm lacking space, I'm using a strange notation here, right? But I guess you get the idea. The bars are just disjunctions, and sorry, no, I didn't do this, and right, so this is a CNF. So when encoding such circuits, there's one thing to consider. It's in constraints is sometimes called arc consistency, and I would call it maybe redundancy. And for an example, consider sort of you have here a gate. So it's like an equation, like you had in the example with the Zetin problem, where we now have a condition, and if the condition is true, then we'll get a true case, so the then part. Otherwise, we get the else part. So think of this as this question mark colon operators in commonly used in programming languages. You can also think of this as if conditioned, and then it's else, or people would also sometimes maybe call this cont something, like for conditional. Or okay, I think I get the point now. The way how you can encode this into Zetin would be, if C is true, then X is equal to T, and if C is false, then X is equal to else, right? Well, the equal sign is now this is low, sort of highest priority now, and then you encode this further. So this is the same as if C implies, then X implies T, and T implies X. Okay, and here it's the opposite. This is, if C is true, then X implies E, and E implies X, and yeah, and then we flatten it as we did before. Because this here is an OR, and then this thing here becomes an OR, and we're going to erase here the negation and put the negation here, and then we can use our distributivity law and also remove here these implications, and then at the end get like 6 clauses, which I'm now dropping the OR again, like I did in this one example. And I get that one, and I get C and T bar and X, and I get C and X bar and E, and C and E bar and X. Okay, so this looks pretty good. Just a sanity check. So like for sanity checking, look at this one. So if the condition is true and the then part is true, then the output of this thing here should also be true. This is also sometimes called in circuits a multiplexer. So where you can have here C as a selector, and then T or else as input, and then depending on C you get one of these two guys, right? max for multiplexer. um, so we now need to discuss the following thing. So if you think about this last one here, then so about this operator, then it's clear that if t is equal to e, right, then of course x is equal, let's say, to t. So and if you think about it, this is a redundant constraint, and it, for instance, would give us here the formula if both e and t are true, right? So both true, then also x has to be true, and if both of them are false, right? False, right? Then x has to be false. So we would have this additional redundant clauses. However, as it turns out, they can be resolved by resolving on the condition here. So if we take this first clause here, this one here, we'll take it here, and move it here, and you take this third clause here, also move it here, and then we'll do a resolution between these two on the variable here not c. Well, then we're getting exactly what we wanted, so we get not x or t or e, right? This is our is the second one here. Okay, and it is also true for the other one. So the message is that if you're these pink clauses down here, they are would give you sort of more power to the encoding, right? Because if you think about it, like the SAT solver knows that e and t are true, then it will immediately deduce from these that x has to be true. However, they can be resolved from already existing clauses, from these original clauses which we're having here, and those would be what we would call irredundant. And therefore, a SAT solver would want to only have these irredundant clauses to keep the formula simple, but it might internally actually derive these redundant clauses, and therefore, depending on like how powerful the SAT solver is, you want to explicitly encode this redundancy, but most of the time you do not want to do it. You can also think of it in the following way. So if you think about, like, you give all 6 to the SAT solver, and the SAT solver needs to has a procedure which determines that well, ternary clauses which are the result of resolving 2 ternary clauses would be redundant, then the SAT solver would remove those and would spend like effort which you could have avoided anyhow from the very beginning. So what I've shown you so far on the bit level, these are constraints which you would want to use to encode execution of a program. But often a problem encoding into SAT also has certain constraints, and these constraints are more of a logical nature, and therefore maybe different methods are needed. I'm giving you 2 examples here. The first one are cardinality constraints. And but of course, like, not really the ultimate explanation for this. And the other one will be something about fixed points. So what are cardinality constraints? Well, we saw already before in examples. So the kind of majority gate is one for over 3 bits, but like the carry out we had before was actually, you can think of is if you take the input bits, right, and you sum them up. So this plus here, this is really sort of natural numbers, okay, natural numbers plus, where you kind of interpret really true and false as constant, right? And then we're asking whether this is larger or equal than 2. This was the majority gate thing. Okay, so in principle, these are called cardinality constraints. So they're kind of linear programs where the variables are 0, 1, and where the coefficient here is always 1, of course. And these are actually all exactly their conjunction, and or like is exactly the set of Boolean of symmetric functions, but that's not the point now. Actually, something which goes back to Shannon I want to show you. Like assume you have this constraint here, A, B, C, D, and you want it to be larger than 2 and smaller than 3. So, oops, 3, and so that means there are at least 2 of these 4 are true, and at most 3. So how do you encode that? Of course, now you could sort of take an approach and think about like ruling out all impossible ways of assigning these variables. But another one, a circuit-like approach, and that's what I'm going to show you here, is based on BDDs. And so what we do is we have here a BDD node. This you need to think of a node here reads this down here with a stroke here. This is the then part, and then we'll have a dashed version to the right, and that's the else part, and in there it's the variable, okay? And then if A is true, right, then we're going to sorry, if A is false, then we're going to check B. If B is false, we're going to check C, and then if D is false, then we know that all 4 are false, and this is clearly a false, right? Then we'll get to a second row, and we do the diagonally the same variables. So BDDs or OBDDs are have this requirement that the variables are always kind of here tested in the same order, and so we're going to do exactly the same again. So we're going with an else to the right, and here we know that at this point we have also 0, because there's exactly one variable true, right? You went down sort of like one way here, and one of these 4 ways, and that's like in most one variables you were not satisfying yet. Okay, now we're done actually with the A's and B's, so now we're doing a C check here. Now 2 are true. Okay, and we still need to do here a D check, and now if we now go to the right, we now know that exactly 2 variables are true. So this is what we wanted. So we can put a 1 here, right? And yeah, right, you see, like for instance, if you went this way, you had like 2 variables, or if you went this way, you have 2 variables, right? All right, now and the same here is true here for the D down here, where if I went down here, then my 3 variables here, which I had in this vertical line, are true. And also, like if you go this way, and I didn't draw this yet, so this would also be true. However, if you make D also true, then you're false, right? So it doesn't fit anymore. Okay, now you're doing, we need to introduce like Zetin variables as before, right? RST and so on, right? And then we're going to encode like each of them as a constraint. So for instance, we would here have that a y here, this y here, we almost cannot read it, so it's a badly written y. Let me try to draw it again. So this y here is such a mux which we considered before. If b is true, then we get s downward, right? And otherwise the t, right? And then we'll continue and get our like 4 clauses, right? So that means we're going to have here, like with this 4, 3, 2 plus 1, 7 plus 3, 10 such maxes, and of course some of them simplify, so it's we don't really need like 40 clauses, but that's the idea. You also see that if you're kind of put here an arbitrary constant here to the right, so let's say we're putting here a k, and these would be n variables. Then this whole thing here is in the order of onk, which could be quadratic, and there are other ways in the literature which make this cheaper, but in many cases this BDD based version I'm showing you is still pretty useful, and at least sort of it's a very natural way of doing constraints. So the next thing I want to show you is related to other types of constraints which are really often, and I would call them maybe fixed points constraints. And a typical example would be temporal logic and the encoding of temporal logic. Sort of, for instance, the reachability of the existence of a path. If you're aware of that, that's kind of a least fixed point. But there are many other examples like reachability in a graph. So think about sort of having encoding a Sudoku, and you want to know that something is reachable, and you also get to these least fixed point. But more abstractly, let's assume you have an equation which looks like that. Okay, again a bad y. Sorry about that. And then the y is like b or x. Okay. Then this set of equations, of course, has a solution. Like for instance, you make a solution for x and y, no matter what a and b are. These like just put x and y to true. So the largest fixed point, largest solution here is for x and y is x and y equal to 1. Okay, but if maybe your semantic of this mutually exclusive equation is that you want to really have the sort of implication of y is the smallest formula, then of course the solution is x of y is the same as a or b. And that's not that easy to encode. I mean, like you could take this and generate like what would be 6 clauses, and but that's not like that's not the correct way of encoding this. Only for the largest fixed point. For the smallest fixed point, you're making a mistake here, and there's a kind of a whole field, if you want, which called ASP or answer set programming, which talks about so-called stable models, where you kind of need to make sure that you kind of not cyclically assume something. So this solution here would be a cyclic solution. So I got this wrong. Yeah, sorry, no, I got it right. And if you want to avoid these cyclic solutions, you might either sort of like dynamically or just to build directly into the SAT solver, detect these cycles and avoid them. For that, of course, you would need to know that for x and y you want like least solutions. So before we now look at SAT algorithms, we're going to look at one more kind of encoding part, and then I let it be. So the question is, how do you get like more complex, like a C program or the execution C program now into like CNF? I mean, we now know how to get a circuit, the bit level circuit into CNF. Next step is like how can you get something more complicated? And for this, let's assume we want to compute the bit vector addition of two bit vectors of length 4. So you can sorry, I should not have written like 4, so it's better to think of this as like three bit vectors which have S2, S1, S0 as bits, like 4 bits, and we add this kind of the same with bits together, x1, x0 plus plus y3, y2, y1, y0. Okay. How do we do that? And the basic idea is that you just need to compile a hardware circuit for it and then take the Satan encoding of this hardware circuit. And then for those of you who went through digital design courses, that's pretty simple, but let me just like briefly explain how this done. So what we're actually doing is we're using full adders, and full adders here are like boxes. It looks like that. They have 3 inputs, x and y, and usually carry in, and they produce a sum out bit and like S, and also like so you can think of this as a carry out, so I call it O. And then we take these full adders and put them together in the following way. So we're having, now first of all I should write down the semantics. So S is then the same as the XOR between the 3 input bits. Okay, and XOR between the parity, all 3 odd, then S is odd. If all 3 even, then S is true. Sorry, if all 3 are even, then S is false. And then we also have this carry out here, which is majority gate, people call it, because it takes sort of the value of the majority of its inputs, but it's also symmetric. So, but you can also think of it as a cardinality constraint, which simply checks whether 2 of them are true, and that's by this big disjunction like that. Now you take what we're now going to do is just taking these full adders and plugging in here the bits. So here we're putting actually a constant 0, and then we get S is 0. Then we get the next full adder, and we're getting S1. So maybe I'll just not maybe draw these arrows, but the others are kind of clear. So we could x1, y1, and yeah, this is kind of the input of that one. So it should go here to the left. Maybe I should have written here this differently and put here the I here as an arrow here from the left. Okay, and then we'll put here a 0 in, and this here is of course just y0. Okay, and then we continue doing like this 2 more times, and then get all the desired output bit, and that carry here can be ignored. Okay, and since all these guys are now just circuits, you just have to like use now that Satan encoding. In this way, you can get like a 4-bit addition. Yeah, you can do the same then, of course, with other operators. Like we would call these guys kind of world level operators. Or if you want, if you're an SMT person, you would call it bit vectors. So what I've shown you here is kind of how do you get the bit vectors or word level expressions into gate levels, which is a classical hardware design problem. And then when we have this gate level, like these circuits, then we can go to formulas. The beauty about this is that you can really do this kind of for all kinds of real executions of machines where you don't really abstract something to something continuous, and that's why this is a very useful technique. All right, so next we're going to talk about actual algorithms. So I would call this P versus DPLL. And I won't talk much about this first thing here. So this is for Davis-Putnam, because this would be preprocessing, and I don't have time in this video to talk about preprocessing. So what we're going to look at is this DPLL, and I assume that most of you have seen this, so I try to be pretty fast here. So again, like in the Dimex notation, I'm going to use now like 1, 2, 3 for x2, x3, right? I guess you get the point, right? So this is kind of x or x3, right? And then we put here lots of ands around it, but let me just forget about this and keep the just 1, 2, 3. Then we're going to have the negation of this second one, and then start over again with the same. I think you know where this is heading. So we're going to really have here all the possible clauses with 3 variables, right? So this should be 16. And now we're going to play I'll try to solve these formula. First of all, this formula unsatisfiable? Yes, of course, it is unsatisfiable for the same reason we discussed before. For the simple example with the mask and the shirt, these clauses here each clause rules out exactly one assignment of 3 variables, since there are like eight such assignments, and each clause rules out exactly one. For instance, this last one rules out the assignment where all are true. This first one here rules out the assignment where all are false. This rules out all possible studies. Now let's do this with a SAT solver, and the classical way of doing this is a DPLL search tree. So you're kind of look, it's like a BDD, right? So you would, for instance, pick here a variable. Let's say we're picking 1 as variable, right? And then we make it true, for instance. So we use the same symbols as in the sorry, as for the BDs in the coding for the canality constraint. Then you see that this first clauses here are all true, right? But here these 4 are false. But nothing happens because there's still, like in all clauses, like 2 literals left. So it's possible. So it would in principle be possible to satisfy them. Okay, nothing happens here. But the next step would be we're going to assign here variable 2 to true. Okay. All right. And now we're getting the situation that these clauses are gone, but it's really kind of strange to actually even consider them. But we're going to have now this clause and this clause where 2 literals are false. Okay. So if for some reason, right, so our SAT solver works by walking downwards this list to find such a case, it would find this clause here first, and then call this a unit clause, and we'll force this guy here to true. So we're actually kind of taking this clause here and use it here to assign 3 to true, and these guys were a decision, but this guy not. So this guy has only one one outgoing edge, as we'll see in a second. So this is not a decision. So, but now we figure out that this clause down here, here is conflicting. So we often say conflicting. So this literature is not clear about that, but it's called a conflicting or a conflict clause. I like the term conflicting more, but let's not go into that. So why? Well, because now this not 3 here is also false, right? And while yeah, this clause is, and the red ones here would be also the 2's here. Okay, I think you get the point. Okay. Okay, now the solver backtracks. So I'll backtrack here by just pressing Control Z. And now we're again in the situation where 2 is true. Then we said we're going to imply 3, but this is okay. So now we're getting the first time to 2 equal to false, right? So now these guys here are false, and the other clauses are true. And then you would see again, maybe with this argument that we get here downward, and then like see this clause here first, where force this to a unit. Okay, so we have the same situation as before. So we setting 3 to true, but not with the second branch, and then get, of course, in exactly the same conflict as we had before conflict. Okay. And of course, this would continue. Then we're backtracking. Then we'll maybe do 2 again. We could also do 3, by the way, but doesn't matter, right? And we'll get also by unit propagation again to 2 conflicts, and that would be would then show that the formula is unsatisfiable. Okay, now let's move on to the core algorithm of SAT solving, which is CDCL. So let's go back to the start of the tree. So it looks almost the same. Also the example here. So if we're assigning 2 to true, right, then we're getting again our conflict down here, right? Okay. So maybe again assigning 3. First to true, okay, and then get the conflict by our clause down here. But now we would say, okay, let's see, what was the reason for this conflict? We made some assumptions, and the assumptions are these 2 guys, okay? So what we really said was, if 1 is true and 2 is true, okay, then false. So I now need to use bottom, because otherwise it's conflicting with the 0 or something. All right, so I guess you get the point. All right, so that means what I really know is that 1 and 2 as a clause cannot be true. All further, this is the same as saying the clause minus 2 is not possible with these with this formula. So once again, is if this is our formula, and this is our new clause, what we kind of showed by F and C, and we nowadays do call this unit propagation. If this gives bottom, okay, then we know that, sorry, not C, I got the wrong thing. We call it alpha, which is the negation of C. Okay, I'll come back to this in a second. To bottom, then we're getting F. F implies C. Okay, alpha is supposed to be not C. And and therefore F is actually the same as F and C. And that's what I kind of did here. So I added here my C. Okay, so revert this until the point where we derived the C. So we now know that this C can be added to the formula, okay? And if you look carefully at this C, then you will see that it's a little bit strange because, well, if you look at this graph here, then at this position here, we made a decision 3, okay? But that's not good because sorry, not the decision 3, we made a decision 2 to be true, but that's not good because if you look at this clause, if you would have this clause here, then this is false, right? And therefore this has to be a unique clause, right? And for not 2. So that means I should not have done this. I should have immediately just after 1 take the unit implication here, this 2 as a unit, as we did it before with the 3, okay, but like now with only one outgoing edge because it's false, okay. So this here is not a decision, right? So this is an implied unit. And furthermore, one thing which might be important here is this clause here, is a learn clause, we call it, and it's responsible here for implication of the 2. So what's this CDCL doing here? This conflict-driven clause learning here. Well, it works like DPLL, but then in a situation like this one, it tries to figure out what are the reasons for my failure getting into this dead end, like my conflict down here, and then I learn the reasons, which is something I can add to the formula, and then I figure out, okay, so if I have this in the formula, and I kind of backtrack and reconsider the way how I get here, then I will figure out, okay, and that's guaranteed. Well, I would not have taken one of the decisions I've done before, right? So you collect all the decisions which led to this bad situation, and then you have to undo one of them. And therefore, this situation, this decision here becomes a propagation of the negation of it, right? So you can see that here it's a 1, and here it's a false. 2 to true, and the right one is 2 to 1. 2 to 0. And this is in principle the idea between conflict-driven clause learning. I mean, we could continue now. So if we do here if we continue, and you will see that as before, that's now of course like these colors don't match anymore. So I'm not going to do this any further. But you will see that then after one more decision, then you will get a conflict, and sorry, not even after one decision. What's going to happen here is this 2 to false, right, which I just erased here, will lead to another conflict. Actually, it will be here a conflict with this here in this particular 2 clauses. So this one is now false, this first one, and then 3 and not 3 are in conflict, and then I will again try to collect the reasons for that, and the only reason we're having here is this 1. So what we're going to do actually next is to learn here the negation of the single decision, which is then the clause not one, the single clause not one. So once again, we have that f and 1 per unit propagation, like looking at these units, will get into bottom, and therefore we know that f is the same. So actually the f prime after adding this binary clause is the same as f prime and adding the binary clause not one. All right, and actually this happens quite frequently learning these units, and we're going to look at this in the code or in the output of the sat solver next. All right, now let's see about how this works in practice. So I have here in the such directly a regression suite which uses these formulas. So this regression suite here is called by this guy like a shell script, and yeah, we're going to look now at this file here, which is a larger one, and it is expected to produce 20 as output as unsatisfiable. So let's have a look at this formula. So if I run it, then we're getting unsat, of course, as expected, and pretty fast. So in 4,000 conflicts. Maybe I should also explain some more statistics here. So this is the number of decisions taken. So you see that there's like way more decisions than conflicts. Why is that? Well, because first of all, the solver needs to is restarting, what we're going to discuss at 1.2, and then you're going to sort of go down and you're making wrong decisions. Then the CDCL has a way of covering up for these bad decisions, and then it jumps over decisions which were redundant, and that also means that you have usually more decisions than conflicts. The next statistic you want to look at here is propagations. This is the number of assignments in essence, and also sort of the number of times you found you walk this list of clauses to figure out whether there's a unit or a conflict. And that's again another order of magnitude larger, and this is very typical. Usually it's actually even more, so like 2 orders of magnitude. And so maybe this already gives you a flavor how this is done. So you're going like really deep. You propagate a lot. Like for every decision you propagate, maybe you assign 10 more units, right? Remember we had this these nodes in the tree in CDCL which have only one successor. These are all propagations, and usually for one real decisions you have 10 of these implied propagations. And also, like, this is really the hotspot of the solver. We'll talk about this later a little bit more. What I want to show you also here is this output here. So first, maybe I need to explain how you read that. So there's like here kind of a header, which is like for this small example barely readable, but I try to explain it. Of course, like we had like 2,280 variables and then this many original clauses, and then initially 100% of the variables are still there, and then this sort of does something, and then it hits the first conflict. So this is, you barely see it. It's really sort of below this conflict header there, and that's the point I wanted to make. This conflict actually leads to learning a unit clause. So that's when this I is printed. So this I means iteration. I don't know why I called it like that, but in my solvers it means you learn the unit clause, and it happens quite frequently, right? You see like 1, 2, 3, 4, 5, 6, 7 unit clauses, 8, 9, and then you're getting close to you find the empty clause, and this is the code that the formula is unsatisfiable. And this already happens for the first conflict. So the solver really went down the branch, and the very first conflict detected was one where, after analyzing the reasons why this conflict happens, you realize there's only one decision necessary to get that, and that's then the conflicting the learned clause. It's negation actually. All right, now next happens here after 6 conflicts, after 5 more, right? We again learn a unit, right? So and also the number of variables is now going down. So for this first unit, we only were able to sort of like make one variable inactive, which is this unit learn. But here we are actually jumping from, you see, 2279 to 77. So we're going down by 7, and the reason for that is, well, because we learned this unit and then we propagated, and only after propagating we actually print this line, and then this learned unit implied another unit, like on the top level, another variable, and that's why even though we just learned 2 units here, we removed kind of 3 variables which we become assigned. Okay, then next thing I want to show you here is this line here. This is the reduction. So this number here also goes up. You can see it also barely here. And this minus, so minus for removing clauses, that needs to be done quite often actually in a solver. So here we do it after 300 clauses. And what's the purpose of this? Well, it removes clauses which are redundant. Not all conflicts lead to clauses you learn. So here you see we have 300 conflicts, but we have only 272 clauses here. Some of them are actually not necessary and learned. And so that means like from this 298, because the 2 unit clauses are of course not added, some of them were removed, and that continues here. So now from this 588 conflicts, only 469 redundant clauses remain, and you see this is going on. So this is number of conflicts, and this is the number of redundant clauses. Okay, right, and of course, maybe another way to think about this is that sort of you're trying to sort of like learn shorter and shorter clauses, because this kind of removes some part of the search, and then at one point, of course, like when you continue learning shorter and shorter clauses, you will learn a unit, and these are these I's, and it really happens quite frequently. Now back to the Blackboard. So one important data structure, if you want, and then it's also an algorithmic aspect of the CDCL, is what I would call the implication graph, and this goes back to Jean-Marc Silva and Karem Sakala, and I'm going to, this is really sort of at the core of CDCL, and extremely useful to get like a fast set solver. So how does it work? Okay, so first of all, we need to kind of maintain the assignment of the SAT solver, and that's usually done with some global variable stack, and it's called actually trail. So like this captures the assignment. And it grows like upwards, so it's like a stack. And if you assign, let's say, a variable 1 to true, variable 2 to false, and so on, then you grow here upward. That's the trail, okay? And then when you make a decision, you might push here 4 on top of it. You can backtrack and then add -4 because it was flipped, well, and so on. And then there's like usually in my solvers it's called values, another global table, and this goes really sort of like from smallest variable to largest one, and it actually is a ternary variable, ternary contents, right? So like these are all variables, right? For all variables you have this, And this just gives you which are assigned. So this is the two key data structures you have. And with that, you're already doing pretty well. Then, of course, like we still need to have the clauses, like this clause here, for instance, and another clause for -6, 1 or so. And work with these, and these are usually also kept somehow in something which is all again indexed by the whole variables, right? And then for each variable it would have like two entries, like one for the false occurrence and the other one for the true occurrences, like the positive and the negative occurrence. You can think of this as sort of actually here it's like maybe variable 1, -1, 2, literal, of course, -2, 3, -3, and so on, right? And then here 1, right, would need to have a connection here, and maybe it continues here. 2 would be only here in this example. This 3 would go here, and so on, right? And of course, like what one really does in practice is to have here actually a stack which is usually a power of 2, so it could be like a 4, for instance, here. And this would then, for instance, this 1 here would be keep a pointer here to these two cases. So I think like this is maybe something one could figure out already by yourself. So usually I would call this case, for reasons which we're going to discuss later, watches. But of course you can also think of this as occurrence lists, like lists of occurrences of a variable. All right, but now we also need to kind of remember how to organize this this learning, and the way, as I said, is the implication graph, right? And this is now on top of what I just showed, right? My way of describing is maybe slightly different than in the literature. So, but I try to make it fit also like what other people do. So here's like the decision level. Some people use here like an @ sign, and the decision level really starts at 0. So here at 0 there are all the units, right? We discussed before. When you learn a new unit, you will go to the top. It doesn't have any decision before it. Just like is something which you need to do because it's forced. So let's assume we're having here, like as in the example, we have here -2 as a unit, okay? And also, like what's in the literature would be, you write here the decision level at 0, and then the assignment. So instead of having here the -1 to denote the literal, which is true, maybe in the literature you often see such a sorry, not true, yeah, because I said like the variable 1 is false, so -1 would be the literal. We would see this notation. I prefer now this one because here, well, the level you see from sort of the separation here, so there's going to be another level here, which is 1, and another decision level 2, and another decision level 3. Okay, okay, there might be multiple. It could be even that sort of like this unit, because there's a clause which has the shape of 1 or 2. That there's another literal implied on this level. So this is not from the example. This is just make this up. Okay, now here at these decision level, we need to make decisions. Let's assume we're making here a decision with variable 5. Okay, now it could be that we're going to imply a literal 7 directly, and this is then because of the clause not 5, 7, right? But we could also maybe do 9, but we need here this unit from the top. And then you see this 9 here actually has as reason the negation of these two guys, which is not 5 and 1 is clause, right? So so this is the convention of this implication graph. You have the nodes, which are literals, so signed variables, and their predecessors, like in this case, the predecessor here is 5 and 1, right? They are the reasons, the antecedents for this guy. So maybe I draw this in a different color. What I mean here is this is kind of the reason clause, right? For this thing here. And this was the reason clause for this thing here. Okay, this is how you read the McLaughlin, but now let's continue building that. Maybe nothing happens here, but we're making for some reason like a decision -6. Then -6 could, in principle, here, let's say with the 7 here, okay, and also with the 9. Get to let's say, what do we have? 4, okay. But that is in conflict, and this is drawn like that with the kappa. And actually maybe we can do this red because it's kappa for conflict. And we also plug in here now this guy. So if we now read off here the conflict, then we'll get again the negation of this guy, which would be not 2, not 7, not 9, and not 4. Okay, so there's a clause of length 4, which is now falsified. Okay, so we're building this tree like we do here, but what would be the next step? Well, we're going to do a conflict analysis, and the conflict analysis here would be as follows. So we're going to consider here this here as a first cut. This cut here through this graph separates the decisions on this side, right, from the kappa. And it corresponds to clause. Now in this case, the clause already exists actually in this background. By the way, so I just forgot, there's this is not possible, so I need to have another line. Let's pick and this line here. Okay, so we need to have here in addition 6. I can't see this. 6 is here. Okay, well, why is that? Because actually what's an invariant here, and that's why I figured it out, is this these two edges are here, these guys here. They're really necessary because there's an invariant in CDCL that, like, when you get a conflict, then there will always be sort of like two literals contributing to this conflict from the same decision level, from this decision level 2. and that's why I figured there's a mistake. And anyhow, so like down, we need to, of course, like have this cut also go over this line. Now, the first step, what one would do is one would try to find whether there's like another cut, right, which would actually do the same thing. And right, so we're cutting here now, maybe here, and that's because we're kind of resolving here the clause of this assignment. So this guy has as reason not 9 and not 7, both from decision level 1, and 6. Okay. Okay, and if you resolve this clause, it's really literally a resolution. So we take this guy here and this guy here. Then we'll get from this the resolvent, which takes out here the 6, right? And sorry, not the 6, the 4. This was a 6. This doesn't look good here, so just a second. So this doesn't look good. So it's a 6, and so the 6 remains, of course, and the result would be the 6. Then the not 2, the 9 is shared. Then the not 7 is also shared, and the 4 goes away because that's what. Sorry. The 4 goes away, and of course, because of the 4 had to be in here, right? Because it's the reason of that. Okay, so if you resolve these two clauses, like the green one and the red one, you get this pink one, this one, and that would be then our learned clause. This implication graphs also have another way, which I'm going to explain now in with a different setup, so less complicated. But so we're going to have now, let's say we're not having any unit that's like just irrelevant for our example, but we're going to have here a decision 1, here a decision 2, and this decision 3. Now let's say like 1 implies 2, and maybe not 2, 4 and -5. What about that? And then 2 does something else, like maybe -6. Maybe actually together here with this 4. And yeah, just like for you, maybe start checking that you you have the right answer. Now let's assume we're going to get here to the clause 5, and then we'll have the conflict, not 5, 7, and we have the conflict with these two guys, and maybe here these two guys. So let me write down the conflicting clause. So the conflicting clause has 4 literals, and let's start like on the top here with -5. So it would be 5, 4, and then 3 negated, and 7 negated. Okay, and now what you can also see here is that there's another cut which I now need to draw differently, actually, which looks like this. This will be the learned clause. We need to resolve here away our, I think I did this green before, like we need to solve away the clause here for the 7 here, which is just 3, right? Like the clause here would be not 3, 7, with this clause, and then we'll get the pink one. If you resolve these two guys, then you get 7 goes away, and we'll get 5, not 4, not 3. 7 goes away, 5. Yep. 4, 5, and 3, and 4, 5, 3. Okay. And that's a nice learned clause. And now what's going to happen is the following. That's the interesting part. None of these clauses here in the in this decision level here. Maybe use a different color. So none of these clauses here in this decision level, literals in decision level, was actually needed, right? So you really see that these two graphs, these two implementation curves are separated. And also, if you look at this clause here, if you think about the decision levels here, so let me try if I can do this. So if you do this blue, if you put the decision levels here, you would see that 3 was on decision level 3, right? This is at 3. 4 was at 1, and this was at 1. So this is the clause we're going to learn, but that clause now has a strange flavor. So actually we'll call, these are called blocks. And you can think of this as a decision level blocks. And the number of this, like the number of these would be 2, and that's called actually the LBD glucose level. Like the number of level, or the third term for it is glue. So this is the number of levels, right? The number of numbers here, unique numbers. It's 1 and 3 here. These blue numbers of levels from the left here, projected on the clause. And this thing has only 2 levels, but it has size 3. So this already looks like interesting, but more. And this is sort of the really cool part here. There is no 2, right? So and that means, if you think about, like when I explained CDCL, what you should do, right? Like CDL learns a clause and then tries to figure out, when did I make a mistake if I would have known this clause already before. Now this situation is clear, right? Because the decision 2 you would not even have attempted, because nor the decision like 3, right? Now both decisions at decision level 2 and the decision level 3 would not have been taken, because that clause actually already at decision level 1 here forces 3 to be true, right? So what would happen here is, and do this now in orange, is that actually we'll learn here this clause and immediately now in orange derive here 3, right? We can do this on decision level 1, not decision level 2. So that means we're completely jumping over these level down here. And that's what we call back jumping, right? To level 1. Well, backtracking would of course be this level, but like the implication graph allows you to figure that out easily, that like you just take sort of the second highest block here, the second highest decision level, which is like this one, and then you jump to that one, and then you force the literal. Okay, there's a third part to that, which I also want to explain, and that's called a unique implication point, right? So now I'm specializing this topic to unique implication point. So what's that? Well, for those of you who have some background in algorithms, so this is sometimes called articulation point, which decomposes a graph into disconnected components. But we're having here a directed graph, and so we'll see how this goes. Anyhow, so now I start earlier, so I will put here decision level. Later, I mean decision level 1, because we don't have any units. Okay, and then we're doing here an implication 2, 3, and maybe 4, and then we have another decision level which is at 2, and here we have a decision. I'm running out of numbers. 4, 5 implies 9, and then we have down here. At decision level 3, we have our 11, and this together with the with a 9 here, and I'm going to, because it's important to see that, I'm going to write down here the clause. It's like we're going to say not 11, not 9, and 7. So I'm going to, we forgot to put the 7 here. And then this 7 has also a shape like this one, so we don't have a, let's say, -8, right? And this gets us in -8 together with this guy here, and this gets us into a conflict with decision level with this guy. So this is our kappa then, which is false, right? And the yes, note again, so I didn't make a mistake. We have this nice property that, like, the kappa has 2 incoming edges from literals on the highest decision level, and the clause would be not for 8, because here we have minus, and not 7. Okay, now what kind of cut do we get? Well, we could have gotten this cut here. Okay, this is what we're going to call later the decision or last EIP clause, and it's the one where the decision is in there, right? This one, this was, this was 11. This clause here has the property that it has not 11, and then not 9, not 3, and not 4. And if I'm going to draw again the levels on top of it for the blocks, you see this is like the first block is at level 3, and 9 is at level 2, and 3 or 4 are at level 1, right? Like 3 blocks. Glucose level 3, right? And where do you backtrack? Well, with this one, you would just backtrack to decision level 2, right? So the backtrack level is, of course, this is the backtrack level, the back jump level. This one. Yep, and we would kind of continue here. All right, now if I do a slightly different cut, so the cut goes here, stops here, so at 7, so you don't resolve here further. I probably should take a different color. Let's maybe use orange again. So I start here. Then I still have to include the 3 and also the 4. So the 8 is resolved away, and then I'll get this. But then my clause here, so this clause would be not 7, not 3, and not 4. And if I again draw the decision levels, you will see we have the same situation as before. We only have 2 blocks, and in particular 2 is missing, right? So that's why our back jump level would be now 1. So that means we can actually back jump here. So once again, so this first clause, the last UIP clause, this one was jumping back to decision level 2, while this first UIP clause here, first UIP clause, allows us to backtrack to level 1, which is of course better, right? And also, so I mean, there's the multiple arguments in this, but the intuition is, of course, you're pruning more search, you're jumping over things which are redundant. A rule of thumb here is that you shouldn't do, or you should restrict the number of resolutions you should do. So only going back as few solutions as possible. But here's like one thing which is important. This cut here has the same property as this is the first UIP, while this one is the last UIP as this first cut. So that means, if you really look closer here at this picture, is that it corresponds to a clause, to a learn clause, which only has exactly one literal on the last decision level, like 7 for the first UIP and 11 for the last UIP. And that's exactly what kind of is important feature of these clauses. So once again, here, this level 3 thing is only happening once, and this is then the kind of property of these learn clauses. And you stop immediately when you, after resolving, when you find the clause which has exactly this property. There is one more thing I want to mention here. You need to find those UIPs, and how do you do that? And the way to do this is actually you take the trail, which we discussed before, which keeps the partial assignments of the stack as a topological order, and then you walk back this order, and this way you can always find this kind of articulation point without much overhead easily by counting how many sort of variables are still here down on this last decision level. And as soon as this number drops to 1, you found your clause, and we're going to look at that in the code next. All right, so now we're going to look at some details of the code. So my plan now is the following. So I'm going to kind of dive down into this function which does the analysis, which just does the same thing what I just did on the blackboard. But in real code. But of course, there are a couple of things which you need to understand first, and these are two things, how clauses are represented, and then how variables are represented. And alternative would have been I just go through sort of maybe literally bottom up, but I thought it's more useful if you just sort of take everything which is needed to be able to understand this part of the code, and then we'll later reiterate. So it's kind of a cyclic way of going through the code. Okay, so let's have a look at this code file. So this is the main library. So as I said, it's written in C, and it's one single file with some comments. So I try to put only comments which try to explain things. So I did not put links to references like in Cadico, but the thing I wanted to show you here is first the representation of variables, which is explained here. you saw the Dimex format, like where we would have numbers 1 and 2, which are in the range 1, and then of course here the maximum number, which can be sort of represented in two complements, so exactly 2 billions. And you can't imagine, it's really like people are sending me really big benchmarks. And yeah, so KeySight, my other solver, has like 256 million variable. That's it's barely enough, but like Lingeling, which has half, 128 million, this has been broken, or this limit has been hit a couple of times. So anyhow, so I think like being on the safe side is with 32-bit, maybe in 10 years we're going to have actually 64-bit indices for these variables. So what you see here on the left is of course the Dimex format, right? So like variable 1, its negation, 2, and this would go here until int max. The convenient thing about this Dimex format is that you have also this sort of sentinel, which is not used, like 0 is a non-valid index. You can also not negate it, right? By the way, this is the same for the only number missing here for two complements, which is int min, but this is completely illegal here, so we just sort of are one number short here actually in the Dimex format of what we could use. Or you can think of it also this way. Yeah, well, there's another variable or value which I can sort of misuse for strange things. This is pretty convenient for kind of sort of negation and thinking about this, and also the examples. However, it turns out in SAT solvers, it's much more convenient to take another encoding, and that you see here on the right. So once again, this is how these variable indices are encoded, while in Dimex on the left, they're just like these numbers, and negation means not. Now the right hand side, you see like this is kind of shifted by 1, and in addition you're kind of multiplying the actual variable index times 2. It's an unsigned integer, so this goes up to slightly more than 2 billion, and the sign is encoded in the least significant bit. And for that, maybe I'll show you again how this is done. Maybe in a blackboard, so you think of if this is a variable index, right? Then these are kind of our 30 to 1 index bits, and the least significant bit here, this is the sign. I think you get the point. This of course then gives us actually, yeah, even maybe slightly one more variable. But okay, one issue though here is that we need to change the kind of invalid value here to something else, and in the code is just like invalid, it's called as a macro, which is this number here, and actually it should be 5 here. This is a typo here. This is a typo, and it's unsigned int max. Okay, so the reason why I'm showing you this is because now if you go through the code, you need to think of terms like these variable indices. They're not like in Dimex, like here on the left, no, but they're kind of re-encoded here in the 0, 1, 2, 3, where 3 is the negation of 2, and so on. Okay, the next thing I need to show you is how, yeah, here's, by the way, this invalid definition. Is here the clause data, and that's a little bit tricky. So forget this link down at the bottom. This is not interesting at the moment. So here's this ID. We're currently using it for two purposes. First of all, it's very useful for debugging, because then you have an ID, and then second, it's can be used as a tiebreaker for sorting if you want. We need to sort clauses during clause reduction, but it's sort of more a minor thing. If you really want, it's probably possible to get rid of this 8 bytes actually, because well, you just need to use a stable sorting function and other things. So but for now we keep it to keep things simple, also easy to debug. So next thing are like flags. I think the only one for now interesting is this one. We're separating the clauses into redundant and irredundant clauses. There's actually a stack in the solver, I can show you this later, where you put the redundant and the irredundant clauses. So maybe you're a little bit confused. There are like 3 words, and actually the 4th word would be original. So what we really say is they're like redundant and irredundant, no matter whether they sort of like how you derive them. So learned has this connotation that you learn them through CDCL. And that's of course not really necessary to know whether a clause has been learned or it has been resolved or some other method shrunken or whatever. It's important to understand that there are like clauses which are redundant, which you can always throw away because the rest of the formula is satisfiability equivalent, or whether these you have to keep it in order not to sort of make a formula which is unsatisfiable, satisfiable. And that's what this bit is for. Of course, like the learn clauses will by default first become redundant. Then the next line here, this glucose level here, this is already saw. This is the number of these blocks. So these were blue blocks in this in the explanation for the implication graph, like the LBD or glucose level. I again use all 3 words. Don Knuth came up with this glucose level. The original authors called it LBD. I like clue because it's the shortest thing, and you can pronounce it. Then next comes the size of the clause, the number of literals. And now comes something tricky, which for those of you who have not seen C might not have seen before. So this is like a trick which really, like I would say, gives you in the order of almost factor 2 speed, and I'll explain this in a second what this is. So let's go back to the blackboard. So we're having a clause, right? And the clause has size. So we have the ID and then some flags, the clue, and then the size. Okay. And now in a classical kind of object, let's say maybe object-oriented way. So this is our clause. You would now have here a reference to the literals, okay, and they would be literals, right? So they are now unsigned, right? 3. So this is 3 is negated. Well, that doesn't make sense, but 4 would make sense, and then 7. That doesn't have to be sorted, right? So this could be 9, and so on. And this is the size of the clause, and however, the problem is these clauses will then be sort of watched, right? And if you now see these pictures, you see these 2 big dots. As I already said before, the main work done in a SATSO is actually propagation, which means walking here these clauses. They usually actually sit, as I explained before, themselves in an array. So you also have a pointer dereference here. But this is cheap. This doesn't happen that often. But this is really costly. So this is costly. This is $. This is probably $. And this is also expensive, because you kind of now have 3 pointer dereferences, 1, 2, 3. While this is still the most expensive one, but this is also expensive, and you can completely get rid of it if you're able to make the array actually variadic, right? And this is works as follows. So you just have here size, but now you continue just here with the literals, right? You put the literals here directly after it. I don't remember what we had. I think we had 4 and so on. Okay, and then you only pay 1, like you pay this $, pointer dereference is gone. So that's the reason. Yep, and the C actually, because it's such a common medium, allows this kind of variadic declaration, which says, yeah, here comes an array, but this array is embedded into the object you're allocating, and well, you need to care yourself how big it is, and when you allocate it, you also have to be careful. Actually, in C, you really have to precisely say how big the memory is you're using. And that's important trick. In the code itself, there's almost no difference because the access to these literals looks as if they would really be like in the first version. But of course, the compiler will realize that this is different and that they are embedded. So kind of you would call this idiom like embedded variadic literals allocation. All right, so this is, I think, what I would need to show. There's some more things which maybe I'll just show in the assignment function here. This assign here, this is like what happens if you remember, like you put something on the trail. So that means we're assigning this literal here to true. And we will remember the reason for assigning these literals. Okay, you will see in a second how this is done with the assignment, right? So this clause is such a clause we just have seen. So this is a pointer to such a clause, a reference. Okay, and there's some over has like extensive logging, which serves as comments, but also like for debugging or for seeing like what's going on. Then here there's a specific check for whether this thing is a root level assignment. If it's a root level assignment, then we record this, right? This actually is just a statistic counter, while this one here, this active, was actually the second next to last column we saw in this output, like when the number of variables goes down because more and more variables are assigned. Then here comes a trick, which is, everybody does it, but it's painful for many reasons, and I cannot completely explain it, but the trick is as follows. As soon as you're learning a unit, like something which is definitely implied by the formula and it's a variable, then you don't need the reason anymore. So it's like you just can forget that clause, because that clause is now root level satisfied by that literal which you're assigning, and therefore it's completely redundant and can be removed from the formula. And that's why we're actually recording this by not storing the clause here as reason at all. In the implication analysis, which I've discussed before, this just means you have to check the level of a literal, like the decision level, because like levels, variables which have a decision level of 0 should be skipped. Okay, then we'll assign the literals. There's like some other trick which is related to that these you actually want to have access to these values, this values array for each variable branchless, and because of that we'll actually duplicate the value in a certain sense. We have in this array, it's not of variable size, but it's actually of twice the size of the number of variables, and it will access it with literals, which are twice the size of variables, right? And then for the negation, where the least significant bit is flipped, you put the -1 for negative, and you put 1 for positive, and it's 0 by default. That means unassigned. In the video, I had a dash for unassigned for the number of variables. Okay, then here you see 3 arrays which do have indexed by the index of literal. So this index macro here really just divides the literal by 2 and gets the 32.1 index bits, right? And all right, so first of all, you remember the sign. So this is a trick. It's called phase saving, which we're going to talk about later when we look at decisions. Then we're going to save the reason of a clause. And that's remember, like for a root level will become 0, but otherwise it's kind of the arrows in the incoming arrows in the duplication graph are represented by this assignment. So this is really beautiful if you think about it, right? So the implication graph we saw is a complicated graph structure, and you would wonder how do you really represent this in a computer. It's completely trivial. You just take a reference to the clause which forced this literal to be assigned. Now you might wonder, what do you do with decisions? Well, with decisions you do the same. They guaranteed not to be on decision level 0, okay? So this thing here is then not 0, but then you just put a reason which is 0, a null pointer, right? Null reference. So you find decisions by not having a reasons, and except for those variables which are assigned at decision level 0, and those are units. Okay, so we will come back to this phase service later. This thing I want to show you, this is in essence the information which is encoded in the implication graph we just discussed. So the reasons are these kind of incoming arrows for literal in the implication graph, because the reason contains, of course, all the other literals and also the implied literal. And that is the solver level, right? You need that for multiple things, like for, as I said, like figuring out whether it's a unit or whether it's a decision. Okay, now comes something, we put something on a trail, so this trail is pre-allocated, so that's why it's not a really push stack thing, but we know that like the trail is this maximum size of the number of variables, so that's why we pre-allocate it, and then we'll put the literal, which was just assigned. It was assigned to true, right? You still see it here in this line on the trail. Okay. Then I want to mention this already now. We also decrease the counter, which counts the number of unassigned variables. That gives us a very fast check to determine whether the current formula is satisfiable, right? So we don't need to go through all clauses and figure out whether they're satisfiable. Only we were going to have a check, like which checks that there are no unassigned variables left, and we propagated everything, and then the combination of these two properties will let us conclude that the formula is satisfiable. Okay, so now let's go to the assign function. The analyze function, which is exactly corresponds to our. All right, so we're going to now look at top down to the analysis, as I said, right? So here's the CDCL solving loop. So you haven't seen actually pseudocode of that yet, but this is very close to like how you would represent it on slides as well. So first of all, you might already see here this 20, which is the code for unsatisfiability, and that's like only set to the result value if the solver happens to be inconsistent, which is a synonym for having learned an empty clause or having an empty clause like original empty clause, right? Otherwise, we'll just have this loop here, and the first part of the loop you will just really do constraint propagation, and again, so we're going to look at that also later. So you will just walk all the clauses of the freshly assigned literals on the trail, and then look through their whether they're unit or whether they're in conflict, and if they're in conflict, then we go to this analysis. What we discussed. If they're actually in unit clauses, then we'll just make this assignment with the function which we also just saw, and then continue. Okay. And then this iterate flag, this is exactly the I we saw in the output. So if you learn a unit, then the solver would implicitly, in analyze actually, set this flag to true so that we can see that in the output that there's a unit learned. So otherwise, and that's what I also mentioned before, there's this unassigned counter. So if there are no variables left anymore, and which are unassigned, so in a sense, like the trail is now as large as it is possible. Okay, all the variables are assigned, and propagation did not result in a conflict because we get here in this else branch here. Then we're done, right? We know the formula is satisfiable, so we set this, and this will actually terminate this loop here which really continues until either the result here is set to 20 for unsat, or the result is set for 10 here after no more variables are assigned and no conflict occurred. Otherwise, we do some more things, including like reduction, which I already mentioned, like for reducing clauses. Also, restarting and then some other thing is possible. At the end, we'll need to pick a variable that's done here in this design. So that's the CDCL loop. So it's not recursive. You want to write down this for this DPLL, it gets a little bit more tricky. It's also possible doing it very similarly, but yeah, it's slightly different. Now, as I said, the hotspot is here, and this is kind of really the core of this CDCL, and I'm going to show how this works in not only the Blackboard now, in real code now. Analyze. And it gets the solver, of course, and conflict. So the conflict is the clause which the propagation found to be empty. Remember, like we had this in this example. So you're doing some propagation, and then there was like one clause which forced 3 to true, and then the other clause says, "Oh, then I'm false," and this false clause is now given as an argument to this function. The goal is now to learn the clause and also do the backtracking and the assignment of the flipping of the literal. The first UIP will actually be flipped. Okay, so we're first getting the conflict level, and if that conflict level is 0, okay, so if we get a conflict on the root level, then of course, like just by the units and everything which is in the formula, unit propagation alone would give you a conflict. So that means the formula is unsat. But well, we came to this point actually without having found this earlier. So we're now marking this as unsat, right, the formula. And then we'll also ask the proof checker actually to check this. And because there's no other literal added to the learn, like the checker, that would mean check that the empty clause is implied. Okay, then you see sort of there's like three data structures, three stacks actually needed here. One is the blocks. Actually, each block is identified by the decision level, right? We had like these blue blocks, or like the 3 to 1. Like in one case, it was only 3, 1, so we could back jump to level 1. Then we would push actually 1 and 3 here on this stack. Then the second stack here, this is the clause we're learning. Obviously, you need to push these literals somewhere before you really allocate the clause. So there's a stack which does that. And then this one here is kind of a marked bit of something similar to graph traversal of the implication graph. So this tells you which of the literals have I marked to be seen. And the reason we need this is because we need to undo these markings later. Donald Knuth in his solvers, for instance, uses time spending to avoid this sort of undoing of the marks, unmarking, and therefore doesn't need this stack. Okay, then we make room for the first UIP. So we want to keep the first UIP as first element on the stack. So we just put sort of an invalid literal there as a placeholder. Then we get the marks. Again, these marks are these mark flags which allow us to detect whether we've seen already a literal in the implication graph, like as in graph search, right? And as you see, these are sign charts. So these are just bytes. So you have bytes for every variable. You have a byte which tells you, have I seen this variable before? And that's what you're using for the marks. Then the levels, we saw that before when we in the assignment. So the levels of a literal start in a big array, and we just kind of get that so they can easily refer to it. The same for the reasons. So these are the reasons we start during assignment, right? Remember, these two guys actually really represent the implication graph. And then for each decision level, we have another flag. So similar to the variables, which is here, we also remember which decision levels have been seen already during the conflict analysis, right? So these guys are per variables, and these are per decision levels. And then blocks here, this is just sort of the those frames which we have marked. So the proxy is in essence actually used to unmark those bytes here, which were used to mark the decision levels which have been seen. Okay, and then we start at the end of the trail. Okay, the trail is almost like a stack. So you saw that in the assignment, we push things onto the trail, like at the end. So we start there. And then, and this is the trick, we're having, we count the number of literals on the current level in the clause we're kind of constructing, which are still unresolved. Initially, like all the literals in the conflicting clause, which are from decision level, are unresolved. And as I discussed before, I made this mistake, right? Remember, there are guaranteed to be two literals in the current decision level in the conflicting clause. So this will be after we resolve, after we start this whole thing with the conflicting clause, this number will be at least 2. And then we're going to sort of resolve a way along the trail, like starting backward from this T here, all the literals we found so far until this unresolved current level here is 0. And then we'll get the UAP, so that's why here at the outside, this is kind of the outcome of this thing. There's a variable called UIP, again, unsigned, and just encodes the literal here. Okay, so we have a reason, it's non-zero, so we're analyzing this. The log function will actually print the reason. Marking this reason as used for reduction, so we're not going to throw away used reasons. And then we go over the clause. You see here that I'm using here C, but I have some macros in place which almost make it look like automatic ranges in C11, but and therefore keep the code actually compact. So what I do here is like I go over all these literals, like we saw this on the blackboard, of this reason clause. Then I'll get the index, get the level of it. If the level of that literal is 0, right, I don't have to do anything. This is I already explained also before. So the solvers assume that everything on decision level 0 is kind of ignored. So you only remember the values of these variables, but no reasons. The clauses are anyhow satisfied, which are these reasons. Then I'll take the mark bit, and the mark bit is either seen. Seen is just 1, or not. And if it's marked, then I have seen that and I can ignore it. Otherwise, I mark it as seen, and then later, because I need to unmark it, I'll push it here on the analyzed stack, on the seen stack, actually. There is some necessity to sort this analyzed stack later with respect to timestamps to keep the decisions in order along the timestamps, and that's why I not only push the index here, the variable index on this analyzed or seen stack, I push with it also the timestamp with it. But this is a technicality which we could discuss maybe later. Okay, then we're analyzing this literal, right? So we're saying, okay, so this one has now been seen. And now we need to have a k-split, and this k-split is like typical for CDCL. If the literal is in a lower decision level, right? So in the pictures I had, there were these lines, right? And then we're resolving below these lines here. And if you now find a literal which was above, right, from a lower decision level, then we're in this first case. Otherwise, if you're below, then we are in the current decision level. And if you're in the current decision level, see what's happening? Well, then we just increase this number of unresolved literals on the current decision level. We've marked it as a side effect, so that's important. But we also need to increase this number. The second case here, when the literal is really like from a lower decision level, really means we're going to learn this literal, put this into the clause we're going to learn. That's what's happening here. Right, just push this into, well, this is one of the literals we're going to put into our learn clause. Note, by the way, this literal is because it occurs in a reason of a clause, and it's not, as we're going to see, the literal which is forced to true. It will be only a literal which is forced to false. You also see here the assertion that this is the case. That is really sort of like the negation already we're seeking, right? So we kind of do here the negation implicitly here, right? By following in sort of an arrow backward in the implication graph, we said, okay, we have to flip the literal, but here, because this literal is part of the reason, it's already flipped. Then we do some bookkeeping here for the levels. As I said, like also the levels are marked, the sort of decision levels which are used, and these are called frames. And so if this not marked yet, then I need to pull in this decision level, I call it in other solvers. So you pull in this additional, and this is bad, right? Remember the example with the back jumping? Like every decision level you omit helps you to sort of keep the sort of the clause sparser. That's also the idea behind these glucose levels, the number of blocks, right? So you want to keep these blocks as few as possible, and that's why kind of this is not. If you have too many of these, this is kind of gives you bad, like not that good clauses. But I want to count this anyhow, so I'll push these. If it's has not been seen yet, this level, I push it on the blocks, right? Like the integer number level is pushed on the block, and it's marked as being used. All right, now this is the end here of going over all literals of the reason, and we'll just have this conflicting clause here as a reason assigned here. No, where is it? Here. So we just take the through this loop, which goes backward over the trail. We'll just have the conflict as reason. So this is kind of a misnomer because it's a conflicting thing. So everything is false in it. Later, the reason will always be a reason for forcing a variable to be true, and it will be the case then that this variable or this literal here has already been seen before, so that's why it will not be pushed, and that's why this like assertion I was just mentioning here is true, because the literal which was assigned to true was already marked to be seen before, and so we're not getting here because the mark was true. Okay, now comes the part with the sort of topological sorting. It's kind of hitting here in this loop. So we're now at the particular trail position, right? And but this trail, maybe the very last variable, right, might actually not have might have sort of be assigned even after the conflict variable, because we're sort of like way earlier in propagating. We have not reached the end of the trail yet in our propagation. And so I'm going into the trail and checking whether this literal was already seen. And if it's not been seen, well, then I just keep on going backward in the trail until I find those literals from the clause, and will take it then. So this loop terminates if I find such a literal which has been seen. Okay, and it's actually guaranteed here. This is what this assertion says, that you will never never have an underflow. You will always be above the trail, and we'll talk about this later. Anyhow, so this is the next UAP candidate here. So it's like a candidate at this point, so you don't know yet. It becomes really the UAP if the number of unresolved literal on the current decision level really drops to 0, right? Because then this one was the last one we resolved away, and then we break out of this loop. Otherwise, we know, or this thing needs to have a reason why. Well, it cannot be a decision, because the decision is, of course, a UAP. So if UAP would be the decision of this decision level, then it's guaranteed that this thing here is 0 after and because of that, you will go out of this loop. Okay, then we found our unique implication point. You can actually get there some nice log message for this one. Then that's what I already said. Like we need to sort of the place where we made room for putting the UIP. That's the first literal in the clause. That's now overwritten with the just found UIP. And then we can log the clause we actually did use. And then comes something, I'm not sure like I have time for that in this video here, which is called clause minimization. We start with this clause and actually we can shrink it. And the shrinking goes also uses the implication graph, and then you get like often a smaller clause which is at least as good as the originally deduced clause here. Okay, now you see also it makes also very simple the definition of blocks. So the blocks are the number of blue numbers we had. Actually, not completely true. At the slide, like you had like maybe the blue numbers 3, 2, 1 in the blackboard, and 3 was sort of the current decision level. That one of course doesn't count. So the number of blocks is because the current decision level is always a part of will always be seen in the conflict, right? Because you just made an assignment on that level. So that you take out, and then you take the other blocks, like the other levels which have been seen, which are stored in this block stack, and this is your glucose level. Okay, then we need to find the jump level. So what's the jump level? Was the second largest level in this among those the blue ones, including the current level, right? So you go through this through your blocks and you find the second largest one. That's what we have here, right? So it's a level which is not the conflict level and where the jump level is smaller. Okay, then there's some metrics which have to do with restarting, which we also are going to discuss, and then that's almost it, except for one thing which we have not discussed at all, and this will be part of the second video, which is how do we actually pick decisions, and that's what's happening here. So we're going to bump variables involved in this analysis, and as you kind of see, it's completely clear what you do. All the variables I have seen there during this kind of backward resolution to the implication graph, those are important variables in my current state of the search, and those I will going to make more important for decisions, and that's called bumping, and we'll discuss this next in the next part. Otherwise, I just backtrack to the jump level. This does nothing else but just unroll, like shrinking the trail, popping literals from the trail until the topmost literal on the trail has this jump level. Okay, and then I learn the clause. And the size of the clause is, of course, needs to be again split into two cases. The first case is that you learn a unit, and then well, you don't need to learn a clause. You just assign this to the at the root level. So that's why jumping back to the root level. Then we do our nice prepare our nice output of the I column, right? Remember CI, right? This is done here because we learned the unit. And we learn this not UIP. By the way, I didn't say that before, but the not UIP, so you have to flip the UIP because you take the UIP from the trail, and on the trail are only true literals. But of course, you want to put the negation of it into the in the learn clause, while for the other clause variables, right, which are part of the reason, which are all false, those you put directly into the learn clause. Okay, now now there's like some important sort of like things regarding watching schemes, which we also briefly touch upon later, and but I don't have time to explain this here. Then we have to watch the clause, then reset everything. Okay, so this was a force tour de force through the analysis function, and next we're going to talk about decisions. Now back to the blackboard for decisions. So decisions actually come in two flavors, and the first one is variables, and the second one is which phase. So variable, and the other one is the phase. So this is already, of course, kind of heuristic. And it is the current one which is employed in the solvers. So and I'm going to explain both of them. Of course, like these are heuristics, because we don't really have any proofs on how to use things here, and right. So you need to pick a variable and a phase, and already separating these two is an assumption. There's like one rule of thumb, which is maximize satisfied clauses. Maximize satisfied clauses, and the alternative to that is, of course, kind of and why is that? Well, because if you're trying to get with a decision as many clauses as possible satisfied, you're getting closer to a satisfying assignment. And if you're done, right, if you reach the satisfying assignment, then you're done. And therefore, like trying to eagerly make big steps towards this goal is guaranteed to either get you into sort of a dead end or soon, or you really find this satisfying assignment. And yeah, related to this one is propagate as much as possible. That's particularly interesting in the old look-ahead solvers, where sort of like you count, if I make a decision, you count how many additional variables would that actually assign. So in a certain sense, you're doing the same ego kind of forward-looking thing by kind of actively kind of going for that. So these are kind of the two heuristics in look ahead. There's also really, like, that's the name look ahead, that you kind of simplify the formula first, so you do this sort of in a two-step approach. Now the interesting thing about this is now this is not state of the art anymore. So what we're doing is called, some people called it relevance based decision heuristics. And with relevance here, we mean your look what was actually currently important. And important, obviously, in close learning are those literals which you resolve away, as we've just seen. These are the scene literals, like these which are pushed on the scene stack during the analysis. Those literals which are solved away. Why? Well, because they were used in a certain sense to derive facts. And maybe and this got us into a big controversy, is but I nevertheless write it down here. This has a flavor of local search for proofs, right? And in particular, if you drop the proofs part here, then I'll get into fight with Karem Sakala and others. But I think this is true. So these relevance decision heuristics and VSITs, it's exponential version of it. It's called EVSITs, and the thing I'm going to show you in code is VMTF. They are all of this flavor. So you're taking what kind of the reasons for things which went wrong, right? And you're trying to actually focus on these things which which went wrong recently. This is a very kind of a human way of making decisions, right? Okay, so let me explain these in more detail. So we're going to do first VSITs. I think now I can remember it's variable score independent. I'll talk about that in a minute. Decay, and then forgot was S means sum. All right, so the sum, so the sum means that you sum it up over kind of all literals, and this comes from the um, from old kind of papers from the 90s and like what people used in CRESP. Um, Here's some, you can't read it, and uh, this independent means that you're really looking at variables, right? So it's kind of redundant, this term, because you're having here this independent this independent here in this variable are kind of uh, um, are kind of synonyms. All right, so let me get rid of this one. And so what is this rel? So you kind of um, increase score of scene variables. This is already the modern version. In the old days, when this paper in 2000 by the friends from Princeton came around, they did it like this was here originally was like the variables in the clause, right? But nowadays it's the the scene variables, and actually more. So and a plus re's and literals, and this goes back to the Maple Solver's re's and literals by, from Canada, plus re's and literals of clause literals. All right, so this is kind of the state of the art now. So as you know what scene is from the code, so you just do your kind of graph traversal of your implication graph, and whenever you need to sort of like go back through such an edge, you mark this new variable as scene, and that's like a variable which is important. And then at the end you have these variables in the clause. They have all been seen by definition, right? But there's some more, like those which you walked over on the current decision level. And then this like plus reason literals here, it's called also a reason side bumping or bump reasons. This is kind of new from 2016. But this thing here, this means decay, and that's really the important. Also, decay, I would call it smooth score of all variables. Right, so what you really do in one conflict step is increase the score of those variables which are involved, the relevant variables, and then decay the score of everybody. And this usually goes in a exponential way. Sorry, this would be only here. As also score variable in an exponential way, and this has very much to do with kind of an exponential moving average, right? Or which is of course a very common technique in machine learning. And so the score of the variable will become actually the old score of the variable plus, sorry, this was exactly, no, it's right, plus alpha, which is the kind of smoothing. This is the decay here. Times the what you predict, sorry, what you got, which is the delta. Sorry, the delta. I'll come back to that in a minute. The delta and the prediction. And now, of course, I got it wrong. So this is here. Now this is exactly the right formula. Okay, now what's this delta here? So this delta here is the whether you actually saw that whether this is a relevant variable. So you compute this score update for all variables, right? This S prime is done for all variables, but then you distinguish with this delta those variables which are seen and which are not seen, and for this seen here, delta is 1 for seen variables and 0 otherwise. And of course, you need to take this reason side here also into account. They would become kind of reason or reason side. Okay, and this delta. You can so from this equation down here, you see this is a kind of an update of the scores, and then so you can think of like all variables go down actually exponentially, smooth go to 0, and the then those variables which kind of are interesting, they pick out, and that was the v-sits. Okay, now the v-sits has this issue that you're going to have to update all the scores, right? As I explained, like S prime has to be computed for all variables. This is costly if you have millions of variables. Every conflict by going through all millions of variables and updating this is pretty, like it's still linear in the formula, but gives you kind of a quadratic sort of flavor thing. And that's why people came up with e-sits, actually the two Minisat authors, Niklas Ehn and Niklas Sørensen, and they have this kind of the number of seen variables is way smaller than the number of variables, right? And this is the argument that maybe we can have an algorithm which only updates scores of the seen variables. And so what they do is actually you add increment to all seen variables exponentially, kind of in a geometric fashion. Maybe I should put here the name of this increment. So this is kind of maybe what would kind of, yeah, well let's call it capital I, and then I prime becomes something like actually what you would do would be 1 over 1 minus alpha times I. So this is in machine learning usually beta, like a number close to 1, while alpha is very small. And so this is kind of usually a number like close to 1 but above 1. So typically, for instance, right, 1.1 for instance. And beta would be 0.19. And alpha would be then 0.1. Okay, this explains kind of how things work. So you kind of, instead of decreasing everybody by 10%, what you do is you increase the bump. This is called then bump actually, so maybe I should have called it B. Bump increment. You bump this every time more, exponentially more. Of course, the problem then is that once in a while, actually quite frequently after maybe 1,000 conflicts, you run out of you overflow here, and in particular you which is initially when I saw this is awkward, but nowadays um, I don't think it's an issue anymore. Also because compilers become more robust with respect to floating point. You need floating points, right? And then you have typically 10 to the power 10e 150 as kind of as a limit where the thing overflows. And then what you just do is, well, you take this biggest score and divide all the variable score by this biggest one. So this was one of the invention of the init classes. The other one is, well, you need a binary heap, priority queue, where you put these scene variables. Okay. And then you always pick from this priority queue the variable which is the top variable with the largest score. And however, that of course has the problem that you can only make decisions on variables which are unassigned, and therefore in original implementations by, for instance, Alex Nadell and also by myself, you would have always eagerly removed all assigned variables, like those which are propagated from the binary heap, so that the binary heap only contains the priority contains only the unassigned variables. But that's pretty costly if you remember. So we do one decisions and then maybe 10 or even 100 propagations. So you need to sort of remove all these 100 literals from this binary heap, which is still each of them a log n operation. And therefore, Niklas Sørensen had this idea, well, why don't we do this lazily? So we keep all variables on the heap. And as soon as we ask for a decision, we pop from the heap with the maximum score until we find the variable which is unassigned, and we assign that one. Of course, then doing backtracking by unassigning the variables, you need to check whether these variables are not on the heap and then push them back. Okay, this is the exponential visits, and this is like what everybody else does nowadays, except for my solvers, where I use a variant, at least like in some part of the code, which is variable move to front, and that's much easier to explain, and I'll explain this one next, and also the implement, and that's why I want to show you this in more detail. So now to this VMTF, or variable move to front, and so variable move to front. So this was first appeared first in the Siege set solver, but has a pretty like old concept, which is this move to front. Basically, instead of using a binary heap, which is a part of, and also this smoothing, this decay thing, we're using something much more aggressive, I would say, and always keep sort of like the most recent variable which was involved in producing a conflict as our highest priority for making decisions. So how is this done? Well, it's very simple. So we're doing also we keep the variables in a doubly linked list. Keep variables in a doubly linked list. Okay, and okay, scene variables are taken out and move to the end. Move to the end. Now the only thing which I still need to say is a search from the end towards maybe we should search from we should call this head end, well, from end to beginning to for a decision, from end to beginning for a decision. Okay. Now this has a slightly quadratic flavor, right? So whenever you make a decision, you're you need to sort of start from the end, searching from the end. So it's like um, unless you can sort of hope that sort of like the variables you need to make decisions on are kind of always staying at the end of the list. This sounds bad. And also the original author Ryan, who for this from the SATS over Siege, didn't figure that out. But in 2015, we wrote a paper on how you can do this, implement this faster, and I explain this now. This is with stamps. So everything I had on the before I raised it is of course also true. So we're keeping the variable W linked list, like we remove variables which are seen and put them at the end, and also we search. But we're keeping a search as cache. So what that means is when we search the list, we remember up to which point we search, right? So maybe we found like a variable and uh, and then we remember like the position in the list where we stopped the search for a variable, and then when we again then start searching for a decision, we start at that position, and this already looks like better. Why? Because well, if you think about like you have like 10,000 sort of like literals, right? So this is my list, even so it looks like a stack, and right, and yeah, and these are like let's say even 500 100,000 variables, right? And then I make a decision here, and then I make a decision here, and if I always start here from the beginning here at the end, and here's the beginning, to find a new variable, like I'm traversing here and checking whether these variables are unassigned, then of course like I have accumulated like quadratic cost if there's no conflict happening, right? So for instance, if you would have a CNF, if really like this queue here has one, and it goes like maybe 200,000, right? And you really have only one clause in your Dimex format which looks like this, right? And so P CNF 100,000 one. Then you see what's going to do, right? So I'm going to go over this list like in a quadratic way, right? So I go from the right and then I search again. And the obvious solution for that is, of course, this search thing, right? So you were just going to have here a search field, which is this one here, and we're having like we just remember the position. Actually, in the code, we're going to remember the variable, because there's a mapping from the variables to the positions in this W linked list. And okay, and then when I need to do the sort of like pick a decision, then I move my search pointer to a next position. Okay, that looks simple, but now comes the problem. What if I have to backtrack, and in particular unassign a variable, right? And it could be that, for instance, your search here is as we have here in the picture, right? So it's here, and but the variable, there's like maybe the variable 17 here, which is unassigned. Unassign this guy. Then of course this search is wrong, right? Because you need to make sure like all the most important variables are to the right, and you need to sort of find the first most important, right? So this is the importance order. To the right is more important, right? So this is most important, and you want to pick the decision which is most important. Okay, Now, how do you do that? Well, one way would be is it's also not described in literature. Well, whenever you backtrack, just put the search here to the end, right? So you could, during backtracking, just put it here during backtracking. But then again, you don't avoid this quadratic example I showed you, right? With that 100,000 clauses. Okay, so what our solution was in the 2010 pointer is to have here a kind of a list of stamps, okay, and these are timestamps where timestamps where you kind of make sure that they ordered along the NQ time. So you can sort of think of this as timestamps or NQ time. The time when you NQ'd something to the right, right? And yeah, and this should be, of course, like be totally ordered, right? So like 1035 and so on, 1000, yeah, whatever. Okay, now the point is, you know that this search here has the timestamp 4, but I'm going to unassign here this variable 17, and then I'm looking up here the timestamp of the variable, and if this is bigger than this one, I'm going to destroy it and move the search here, right? Yeah, and that's it. Okay, in this empirically, so I don't have a theoretical analysis. It's really very fast. So it's way faster to than actually the code runs faster than the binary heap code. It's also easier to implement actually, because you don't have to implement the binary heap. Maybe more to this. Offline, but like you need to integrate this heap into in the SAT solver. For instance, the standard priority queue in an STL doesn't have an update minimum, because you need to search. They always work with minimum, so you need to pop during update, like we compute our score as prime all the literals. So you need to probably implement your binary queue heap yourself. It's not that a big deal, but still. And yeah, and then the unassignment in this case is really constant time. I mean, the search might increase, but the unassignment is constant time. You just take out, like in this case, for instance, you would take out if it's bumped, right? You take out the 17 and you move it to the end. And you might need to update this search pointer. While in the with binary heaps, really, so that you have to, even though you use this lazy trick I mentioned, you have to push back, like, to the binary heap all these variables which are which become which were taken lazily, like from this from the heap. They need to go back, and this is really like a log n operation every time. And if you have a million variables, that's still quite substantial. If you have to sort of push back like 10 or 20, 100 or something. Okay, there's still like one issue. So I mean, this thing, as I've said already, this is really aggressive. Okay, what do I mean with aggressive? And well, if you think about it, like the factors we discussed before, so we had like beta was 0.9, right, or alpha 0.1. They could, in principle, simulate such a variable move to front Q with actually alpha equal beta equal 0.5, right? This gives you almost the same effect, except, and that's like if you do this with a binary heap, you will just increase the pressure on this binary heap. Way more things will be bubbled up and bubbled down the binary heap than with a smoother decision, like a smoother decay, like with 0.1 or even 0.01. Okay, so it's not advisable to simulate the variable move to front with a binary heap. Okay, that's one issue, right? So you cannot really do that. On the other hand, it turns out that for satisfiable instances, you should not really be aggressive. So you should kind of accumulate the knowledge about which variables are interesting and not just really focus on the most recent ones. I mean, this is intuition, there's no proofs or something here, but this is kind of what's important for satisfiable instances. Once again, in satisfiable instances, it seems that you want to be sort of more stable, and that's also why the solvers, my solvers have, and also like Thin's Chansik O solvers have a stable and like a focused phase, I call it now, or focused mode, where you switch between the two. And in the stable mode, you're better off using a non-aggressive, sort of like very low alpha uh, decision queue, and in this case you should not use VMTF. But in the other phase, in the focus phase, which is particularly important for unsatisfied instances, almost, let's put it this way, for very very hard satisfiable instances, maybe two, then you should be extremely aggressive and localize the proof search as much as possible, and that's what you get by VMTF. And in addition, you get also the benefit that the actual implementing heuristic is cheaper than with this doubly linked list than with the binary heap if you use this stamping trick I just explained. Okay, we're going to look now at the code for the stamping. So first of all, there's like this just a standard implementation of the doubly linked list. Now, with instead of pointers, we're just using the variable indices as next and previous fields, right? This not only this makes it a little bit more faster, so it avoids like 8 byte, so it only needs like 4 byte instead of 8 byte. And also we can resize this link array without sort of fixing pointers if we increase the number of variables of the solver. And beside this sort of classical previous next fields, you have this timestamp I discussed. So this is the timestamp when this variable, if it's on the queue, was enqueued, right? And the queue itself looks like this. So we have the first and last as a head and tail, if you want, of the queue. I call this begin here the first and call the last end. So this is where we start searching towards the first one. This is the position of this is the variable which we found last in our search during searching for a decision, and when we search more to the left to the less important variables, then we update that so that next time we search we don't need to start again from the end. And then this stamp here, this is the timestamp, which is the number of times I unqueued something onto the variable. Of course, this is, as you see, I've also put this into like 4 bytes, like just roughly after 4 billion stamp operation. This will overflow, and then we need to call this restamp operation. And so the overflow happens down here, and this restamp does nothing else but going over that link and then really just put fixing the stamps that everything on the queue is in order again, and then really just because this happens so rarely, like really only every like 4 billion times, we'll just put the search cache here to the end, and well, the queue is emptied. Now here, this is where this happens. As I said, like the timestamp there is a 4 byte, like 32-bit integer, like after 4 billion times steps or so to the power like 32, that will overflow. But it's an unsigned, so it's like in C actually well defined, and then we will go here into the second part where we restamp. Otherwise, we'll just do this following check, that whether this literal enqueue is actually unassigned, and if it's unassigned, sorry, if it's unassigned, and if it's unassigned, we of course need to update the search pointer to the end. Okay, the DQ version does not any of the special code for handling this, and now we can go to the actual bumping. All right, so this is the code we saw before already, and it's really the scene stack. This again, these are the variables which we see during conflict analysis. Plus, optionally, not in this code, but in other solvers, you can also bump the literals in the reasons of the variables in the learn clause, which is actually a good idea. And then you're just bumping. What does really bumping mean? Well, it's just dequeuing all these variables from the queue. This is a constant time operation, and then queuing it, right? This is not for the bumping. This is just for unmarking the sort of like scene variables. Okay, that's almost it. So there's like one catch though, which is maybe, yeah, this is like something you pay for this using the VMTF. It turns out that the basic scheme I just explained can be improved, and it actually, unfortunately, substantially improved by making sure that when you take out these variables, right, like maybe these guys, and then you put them to the end, right, then you put them in the same order. You don't reverse them, right? You put them in the same order. Actually, it is even more clear if you kind of interleave, you take them out in the order and you put them here at the end. And this really gives a boost heuristically, so the heuristic gets better, right? It's nothing with sort of the time spent in this updates. No, the heuristic gets better. It's important. It seems to be that you should keep the variables sort of in the same order as they are, kind of keeping the order stable, which is a little bit counterintuitive to the idea of aggressive bumping with the VMTF. Okay, and well, that's why you need to you should actually sort these analyzed variables with their timestamp time, and you saw this before. This is where why here in the conflict analysis we're not only pushing the variable index on this stack of scene variables, but unless this macro end sort here is true, where it's disabled, this sorting, but also the timestamp, and then we'll sort these pairs of variable index and timestamps with respect to the timestamp. Okay, and then we bump, of course, as you can see, after it's sorted here, we're really going from the smallest timestamp and take that out one first and put it at the end, and so on, right? So you always keep sort of the relative order between these guys intact. This is the implementation of VMTF. So let's go back to the CDCL loop. So what you understand now by now is this Boolean constraint propagation. We looked at analyze. This iterate was, of course, this minor thing for printing this I. What are two things which are like sort of in the all solver missing and are important are this restarting. So you only get into this restarting if you didn't find the conflict through propagation and there's still unassigned variables left. So in principle you would want to use this decide down here, but at this point you can also decide to restart, unless it's again with a macro disabled, or it's yes, the switching, which we have not discussed, or this reducing the database. Okay, so decide we've covered yet. We're going to do now the restarting. So restarting is really comes from a completely different sort of like motivation. In local search, it was shown in the end of last century that like if you run say anything which is kind of a random component, for a while you might get stuck in sort of an unlucky situation. And while on average it's actually possible to reach the goal fast. And because of that, it's good not to get sort of like stuck in that situation, but to kind of restart and this way proceed. The interesting thing is that the motivation today is completely different, and we haven't completely understood that part yet. But like there's empirical evidence that it's exactly the opposite. So has nothing to do sort of with search in the sense of the assignment space. However, it might still have the same motivation if you think in terms of sort of local search for proof, and you might end up sort of like focusing too much on this way of proving something, and maybe there's another way, and therefore you should have a chance to restart. Okay, restarting itself is pretty simple, so let's have a look at that one first. That's very simple, so we just backtrack to decision level 0. What I have not implemented yet, maybe until a couple of days later, is something which Marijn Heuler and students came figured out, which was reusing the trail, and then sometimes you don't need to backtrack really to the top. So this second argument to backtrack is the maybe you remember it was the jump level in analyze. So here it's the 0. Of course, you go just really to the back. Why is this not harmful, you might argue? Well, because we don't do anything else, so we only backtrack, right? So we keep all the learned clauses. We in particular keep the scores of the variables, and now comes another part. We're kind of here in the default situation. So this has to do with this switching, which we're probably going to explain later. You're really increasing this interval between two restarts. How are these intervals measured? Well, they are measured in the number of conflicts. So you see it here. So this is the limit for the restart, and it's set to the current number of conflicts. And so you saw this also in one of the columns, plus this interval. And this interval here, that's actually here has a slightly increase here. It's log n. In classical solvers, this would be geometric or arithmetic. But since glucose, people actually get kind of a constant interval, and why this is possible, we'll discuss in a second. In stable mode, we'll use a more classical one, but I'll talk about this later, right? So that's really all. This is like what happens in restarting. You in essence just backtrack to the root, well, you try next restart some restart interval again. So like if you spend like 1,000 restart, this is log 10 actually here, rounding up, then you're having like an interval of 3 and so on. Okay. The interesting part here is not like what you do, but when you do it. Okay, so that you remember in the CDCL loop code there was this if restarting then restart. So this is the restarting function, the trigger when you restart. Okay, so you don't restart if it's the decision level 0 because you're already there. Then you check this limit. So this kind of says, okay, the rest of this code is never triggered if you haven't hit this limit. So you wait at least for a couple of conflicts, but not that many, right? So yeah, as I told you, right? So like maybe 3 or 4. Okay, then comes something completely a little bit, or it's maybe obscure, but it can be explained, and that's like the main purpose of this part of the video. So we're going to check the average clue, and that means like just the clue of the clauses which were learned recently. So there's an exponential moving average behind that, and I'll talk about that in a minute. And we have two such exponential moving averages, a fast one and a slow one. And and maybe I'll show this on the blackboard. So you can think of this as like in stock market analysis. So if you have here the time, right, and here's the price. Then what people do in stock market analysis, they measure like a slow moving average, like something like that, right? So this is a slow moving average. While of course, like the real data, like looks like that, right? I'm not sure I got it right. So this is slow moving average, and then they do another one, which is you see a small isn't like the actual data, right? But it's like a faster moving average than the slow one. So this is a fast moving average. Here at the end, I didn't get it right. Okay, and then in addition, they would have a margin around this thing where sort of you say, okay, so before I have here an event which forces something, I want to see a margin. And okay, so the events are, of course, these places where these two lines cut, right? So here and here and here and here and here. But and then in stock markets you would sell if yeah, like here in this event here, because it's like the long average, like the lower, like fast moving average seems to go over the long average move, so people are selling. So it's likely that the trend will continue, and you do the opposite. So like if here, for instance, like maybe a couple of days later, where you're cutting again this line, and then it's the opposite. So of course, like my drawing here is not accurate, but you get the point, right? So you have this fast moving average, and maybe to make this more concrete, I think in stock market analysis they really did like 6 or 9 days window, and I'll explain it in a second, of computing the averages over the last 6 days, for instance, versus computing it over a month. And this is like a real average, like in this window. What you can also do is an exponential moving average. So it has exactly this formula we saw before for the variable, for the exponential visits, where you then do the alpha is just 1 over the days, right? And so if you have for 9 days, it's like 1 over 9, and for 30 days it's 1 over 30, and then because this alpha actually gives you the correction of the current score. In that case here it's like, maybe I write down this function again. It's like plus alpha times, now this would be your kind of price, and this would be your current value. Now like the fast version would be 1 over 9, while the slow version here would be 1 over, let's say, 29 days or whatever. Okay, so this is how you can compute it without a window, and we're going to do this also in a SAT solver. And I think I'll have like 1 alpha fast here is 1 over 0.03, and the alpha slow was, if I'm not mistaken, 0.0001 or something. So we'll look in the code to make this precise, but in this order, right? So this was like 3 e minus 2, and this guy would be 1 e minus 5. Okay. Okay, so the rule is, if the glue measured this way is reasonably, so you take a margin. Actually, the margin is like some percentage of the slow moving price, or the slow moving clue. If the slow moving clue plus some sort of fraction is lower than the a fast moving clue, then it seems the clue is going up fast, and then that's not a good sign. And then we restart. That's the idea. And that kind of allows empirically to sort of control the point where you want to restart, and do only restarts where you not like in the period really making progress, the glue goes down, and you really sort of like think, okay, so this is strange. I'm in a situation where I'm going up and up and up, and maybe I should really restart and see whether I can find kind of more locally proofs with restarting. Okay, now let's go back to the code and see where it is happening, right? So here you see the unbiased fast-moving average. We'll go looking into this function soon. Then here's the slow-moving one. So these are just like in the previous picture, the two averages, the white one and the green one. And then we're multiplying this thing by a factor like 1.25 actually, and then we'll get the limit. So let's maybe start looking for these constants, because I promised this before, right? So here we see the restart marching is 1.5, as I said. Like if you're 25% over the slow moving glue average with a fast glue moving average, then you restart. And then this is, as I also like had on this on the blackboard, 3 times n 10 to the power minus 2. And the fast moving average is actually a slow moving, the alpha for the slow moving average is defined here. Now, yeah, what about this unbiased thing? So this is something I figured out recently by reading some machine learning papers. And it turns out that these exponential moving averages are really are brittle in the sense that they're biased towards the initial value, and of course we start with 0. So this means that, for instance, the slow-moving glue rate, it would really ramp up very slowly to sort of the real average, and you want to fix that. And in our paper where we described this first, also in 2015, how we do this. And also, like in mechanical implementation, we didn't figure out a nice way of doing it, I have to say, at least no theoretically justified. But there's like a nice paper, machine learning paper, actually a famous machine learning papers, which is about the Adam method for learning meta parameters. And part of that is a section where they talk about initializing exponential moving averages. And so what they simply do is, you remember beta is just 1 minus alpha. They multiply the computed exponential average with this term, and then that they give an analysis, which of course is a little bit too above my limit of understanding of the statistical part. They claim is then unbiased, and it really looks pretty good. So I looked empirically, a little much better than the solutions I have before. And what you see is really sort of like the exponential, sort of like without any of this initialization, this exponential will wiggle a lot and actually overshoot like what you really it should be. With this thing, it really very fast triggers on the kind of intuitively, visually the right exponential moving average. Yep, and this is the formula we saw before. You see in C, it's even simpler than on the blackboard. So is still here, right? This blue one, and it's exactly the same. Why is it in C easier? Because we have this plus equal here. But otherwise, it's exactly the same. And then here's the unbiased one. Well, you probably want to cache this 1 over minus beta to the power n, right? Because that's expensive to compute. These are floating points. And this this is just done by keeping beta, caching beta of n, over n, where n is the number of updates to this exponential moving average. And next time we do it, we just multiply this cached value by beta, which is, of course, here it's like even pre-computed as a constant. Okay, and that computes these averages, and yeah, for the restarts, let me just mention here. Jansik made this observation. I think I mentioned this already before, that you should keep your solver into two modes. One which is more sort of has many restarts, and one which has less restarts. And the later is actually good for satisfiable instances, while the former is good for unsatisfiable. As I said, it's the completely opposite as the original motivation, maybe except for this point with the proof search I made, that maybe the same argument from back then applies to proof search, where you sort of like should switch to like new parts of the search space. Okay, so and how do you keep this apart? The current code does this as pioneered in KISAT. So you measure, in some sense, the virtual time spent in the focused mode. The focused mode is the one where you kind of aggressively restart with this glucose style restarts, but with exponential moving average, which I just explained. This would be this else part here. And otherwise, if you're in the stable mode, right, which is only enabled if mode switching is actually compiled in, then you're doing a slower restart scheduling. And in KISAT and Critical, I'm using the Luby schedule. Maybe some of you know that one here, because I was too lazy to implement it, the Luby or Donald Knuth's reluctant Dublin version of it. I just fall back to my old Picosat inner and outer scheme, which actually, for instance, is still used in my copy here of Z3, which you will figure out if you enable the Bose mode. Okay, so this inner outer works by kind of going up to a sort of the outer limit, and you go down and you start again the inner minute exponential up, like more like a sawtooth change, but it's like an exponential increasing sawtooth chain, and the inner outer factor here gives you the sort of the increase exponentially. In the original papers, this 1.1, in the current implementation is actually 2.2. Okay, so these are then the modes of restart, which means like far less restarts in the stable mode. Now the question is still like, when do you switch the mode? And as I started to explain, this is happening here. So the standard, the solver starts with the focused mode, so it will be in this line, and always check them. So then it's conflict control, and these conflicts will increase like in a arithmetic way. And then during this time where you're kind of in focused mode, you compute the number of ticks. This is then sort of similar to Knuth memory accesses. So it's kind of a virtual time to measure how much time did you spend here in the focused mode since the last switch, right? And then next time you run then in stable mode, you're trying to use the same number of ticks. Why don't you use the conflicts? Well, it turns out that in focused mode, because you're restarting so aggressively, your conflict rate per second goes dramatically down. I saw cases where this was a factor of 20, and so measuring the conflicts, or using the conflicts, is not good, because then you spend sort of like 10 times more time in the focused mode, and it's not what you want. So that's why kind of we're giving here the limits, conflicts limit for the focused mode, and then use the ticks computed in that as a limit for the stable mode. And that's the similar actually switching between a stable and, which happens here, stable and focused mode, which is in KISA. Now this is simpler here, but otherwise it has a kind of the same part. I want to show you this also running, so we need to a slightly larger example. Let's try the biggest formula, which is in the repository, this one, and so let me scroll up here to show you this thing. Okay, so this curly parentheses, they start a focused mode. It ends here after exactly 1,000 conflicts, right? Then the stable mode here with this bracket here ends here, and this difference here is measured in ticks, not in conflicts, right? Now, for this instance, could be that it's actually almost the same, but in general, it's not. And here you, for instance, also see that in the stable mode only did like one restart here from in this whole phase, which is of course not much, right? All right, so that's the stable and focused mode. And yep, this splitting of the two modes into stable and focused, together with having actually an exponential V-sits decision heuristic for the stable mode, which we don't have in this Sach solver yet, really gives very good results on satisfiable instances, and you get an additional edge by doing these target phases, which I will not explain in this video. This concludes the part on our on this mode switching and the restart. So we're going to talk about clause database reduction next. So now let's have a look at reduce. So once again, it works in the same way as this restart. So we're having a trigger for when it's happening, and I'll talk about this later, even though like the trigger is simple, but like the limit, setting the limit is interesting. So I'll talk about that. And then we have here this function which reduces the clause database, right? And so what does reduce mean? Well, you have these learn clauses, and with every conflict you put a new learn clause, and they're kind of in the range of the length of these clauses are sort of like 30, 40-ish, but sometimes even way longer, like 100,000 even, or 10,000, or like you have instances where regularly every clause has 10,000, and you need to like propagate over those clauses. And we'll later see the at the end of this video, I will talk about sort of data structures for watches, which is important for getting this fast. But still, right, assume you can do propagation fast, you still need to sort of like propagate sort of somehow in the order of learn clauses, right? Because otherwise you would not need them. And therefore, these clauses need to be removed, in particular those which are which are kind of useless. And this term used and useless is of course interesting, like which kind of heuristics do you use for that? In the old days it was really like that, so you could remove maybe all clauses which are longer than 20. This was in the early set, so one rule. Then the other rule would be, well, you put an activity, this was in Minisat the rule, so you would bump clauses actually, which is a kind of flavor of use, right? So you're bumping them actually with a very low alpha, so like 1 to the power -5, like this low clue alpha we saw, and this already hints towards that sort of this bumping is not that important. Maybe the sort of the age when you did learn the clauses is more important. In particular, sort of like maybe more recent clauses are more useful, right? And for that, it's unclear whether you really need the bumping. Anyhow, so this was pretty difficult for a long time to get right. Heuristics for, but then there was a paper by the glucose authors, Laurent Simon and Gilles Audemars, who talked about, who figured out that okay, I have an a priori metric, which is the clue, which we looked at already, which gives a very good estimate, at least like sort of for the first tier actually of clauses you want to keep. So what they showed experimentally is the usefulness of a clause, it kind of goes down exponentially with the clue. And so you want to keep clue, small clue. Actually, clue of 2 are always kept as by default, where clue of 2 is more, it looks like a like a ternary clause, because clue of 2 means like a clue you can interpret as is the number of decisions you need to make this clause propagating. Okay, so this is on the lower side, so we keep for sure all the clauses which have at most clue 2, and then what do we do with the others? Okay, like first thing, yeah, you need to protect the clauses which are reasons. You cannot sort of like pull out the reason from a literal which is on the trail. This is this thing. Then, in this implementation, we combine reduction also with removing root level satisfied clauses. And of course, you only need to trigger that if there are new root level variables. So that's done here by this fix. So if there are new fixed variables, then you also mark irredundant clauses as garbage. Otherwise, you only work on redundant clauses for this clause reduction. And actually, this solver here separates the redundant and irredundant clause in two separate stacks. And then this makes things a little bit faster. But it's not completely true, because the most sort of the costly, the hotspot in this reduction is actually updating the watch list. And we found a way around this in KISAT, but I'm not talking about that here. And by sort of like splitting in redundant and irredundant, you do not get rid of this hotspot of kind of flushing the watches. Anyhow, then this is the sort of main heuristic. We'll talk about this in a minute. So we're going to gather candidates, right? We don't put on this candidate stack. This is a stack of candidates here. We don't put on it like clauses with clue 1, 0, or 2. Then we sort these guys. Then we mark garbage candidates. Like there's heuristic involved here, which means like these are now sorted. So some of them are more, some less useful, and then of course we throw away these less useful clauses. And how many? And in the original papers, they've thrown away half of them. I throw away 75% for another reason, which I'm going to explain next. Yeah, and then as I said, this is the hotspot, because you kind of you now need to walk this occurrence list and then access clauses randomly in memory, and that's because you need to remove from the watch list these references to these clauses which are removed, like either satisfied or reduced, and then you can go through these stacks, irredundant clauses or redundant clauses, these two here, which and just really physically remove the clauses and flush the references in them. Okay. So that's it. And then, well, at the end, you're going to unprotect the reason clauses again. So now let's have a look at these three. So first one, like gathering the candidates, like I already explained this a little bit. Then sorting them. Yeah, I haven't talked about that. And then you also need sort of a policy for which to keep. So let's first look at gather reduce candidates clauses. That's it. So we go over the list of all redundant clauses, right? And this is the stack, or the stack of all redundant clauses. And then we need to skip these protected ones, which are like reasons. And then we might optionally want to like also check whether the clause is satisfied, but only if there are new root level assigned variables, since the last time we did that. Otherwise, and this is really after like many years, like the local optimum, I'm in there, and there's a paper by Kuldeep and Mate also at SAT 2 years ago in Lisbon, where they kind of through machine learning came almost to the same conclusion, but I heard they have updates on that one, so I'm curious about that. Anyhow, so what's this? There's a Boolean flag I have in each clause. We saw this maybe before, and this Boolean flag tells you, has this clause been used in conflict analysis, right? If here, right? So if you analyze a clause during this, we discussed this loop extensively before. So we went backward, like all these literals are false except for the implied one, which was marked recursively reachable from the conflict. Then we call this clause also as useful because it contributed to this conflict, right? And we had to resolve it away to get to the first URP clause. Okay, this is this flag, and we're getting the value of this flag here. This is disused, but then we reset it, right? So whenever we do a full clause reduction, we reset these used flags. So that means we're going to only sort of look at was this clause used since the last time this reduction was running, okay? And if it was, well, we don't put it as a candidate. So you kind of keep always clauses which were used since the last time we did a reduction. Yeah, this is the thing I already mentioned. So we have this reduced clue limit, which is constant, and this is 2. So if the clue is smaller equal than 2, we'll also not consider it a candidate. Otherwise, we'll consider the clause as a candidate. Okay, so this is the gather redundant one. Next one, after we have the candidate, we have to sort them, and this also has an interesting heuristic. It uses here this comparison function. So actually, when we later remove useless clauses, we start at the top of the stack and pop from the top of the stack. So to the right are those more useless clauses, and to the left are okay. Now we get these two clauses. So this is quicksort. Maybe you don't know how C works, but C has a built-in quicksort, and this has a little bit strange usage. So you take a function which returns an integer, and if it's -1, then the left argument is supposed to be smaller than the right one. So whenever I return here -1, like for instance here, then the first argument is smaller than the second one, and with the explanation I just made, it means that the clause is considered more important than the other one. So here a smaller clue is considered better than a bigger clue, and D has a higher chance to be reduced, like recycled. And in the other direction, if C is actually larger, then you swap the two. Then next, that's a classical example. We have the size, and the size is working the same way. Smaller size is better than bigger size. You want to keep clauses with a small size. Actually, you can just do that. Okay, and you will get not a bad solver. It's with this used and all the other things actually slightly slower, but uses less memory. Well, because you focus on these sizes first. Actually, the very low clue, like this keeping always like clue 2, and also the used ones, is more important than variations of this scheme. At least this is my experience with experimental data. And then here at the end, we're kind of, the idea is done in a sequential way, like it's like a 64-bit index, and this way you kind of take also the age into account. So older clauses are, one means like less useful, right? Okay, and otherwise this makes it kind of also deterministic with respect to different implementations of QSORT, because it's non-stable in general. By the way, we use this QSORT also for sorting these stamps, right? But there the stamps are unique, like all the elements on the decision queue have unique stamps, and therefore their stableness of sorting is not an issue. And then last but not least, we have here this mark garbage candidate, and what you see here is very simple. So we just pop from the stack of candidate candidates until we reach the target, and the target here is computed with this reduced fraction here, and should have no. Okay, reduced fraction here, and this reduced fraction here is 0.75, if I said. So that means like 75% of the clauses are removed, right? Because 25% will remain. Okay, but then what you really do here is only setting the garbage bit flag, because they are now still need to flush these watches, which is, at least for reduction, a very like a hotspot. Okay. So this almost completes our part, but there's a very intriguing and interesting part left, and this is when we reduce. Okay. And it looks very simple. Okay. So we just have a limit, which is measured number of conflicts, and yeah, if this is hit. But then, of course, the question is, how is this reduce conflicts limit set? Okay. Okay, so by the way, so you see here, before I explain that how you remember the last number of fixed variables at this point. And so here's it's set, right? So the reduce interval is a fixed limit. Is 300, starts with 300. After 300 you do the first reduction, and then in principle after another 300, but it's actually increased with a number of reductions. Like with the first reduction, it's like well, it will be 1, and but then it's almost linearly increased, and this is what the original authors of glucose proposed. So they would have kind of done this, right? Just reductions. But what I figured out in KISAT was that maybe you want to actually have a sublinear increase of this interval between two reductions, between two minus signs in this picture. And this reduces, of course, this will throw away more clauses, and this speed up the solver. And it turns out that this seems to be a good compromise. At least in KISAT it was. Here I don't have really complete experimental evidence for that. But so you take the number of reductions and you divide it by the logarithm of reductions, and this gives you a slightly sublinear increase of this interval instead of the interval. But note that already the linear one, like the one I said, right, this one here, this was a big improvement when the glucose paper in 2009 came out, and this became only possible by having a better a priori metric for which clauses to keep, like in particular the one which says, yeah, well, keep all the clauses which have at most a clue of 2. Okay. Anyhow, so I would say getting to this point and really figuring out how to do actually and schedule these reductions with minor variations was one of the big improvement in the last 10 years, together with this Johnson-O idea of getting the like phase saving and mode switching and not mode switching, and on the solver side. And yeah, maybe these target phases, which I will not explain here, and they're also not implemented yet, which I presented with Matthias at the post workshop last summer, actually in 2020. And there's the video and also slides of it online. We're actually working on a journal paper. So this seems to be, it's hard to evaluate, but it seems to be giving you quite some edge also, as the competition results from last year show, where not only KISAT was making a big jump, but also to other solvers which implemented similar ideas. But I won't describe this in detail. So next, I'm going to talk about some other very important aspects of this SAT solving, which is like data structures for watching clauses, and we'll talk about that next. All right, so now we're going back to the blackboard for one important part of SAT solving, which well, at least gives you a factor of 2 more in the range of 3 and 4, and this is about like low level data structure. It's also very important to think about that in order to save memory. So the SAS solver we discussed so far is actually not that good. So it has like 4 to 8 times more memory than the KeySat, and but that also applies to other solvers like Cadical and also Minisat. So what I'm talking about, something is called watches, and this is like a really intriguing idea. When I first saw it, I could not believe it. So I had to kind of I saw the paper, and for 2 days I tried to disprove the authors, but they were right. And so of course now it's natural to me, and now it's my task to explain this to you. So to you, maybe some of you have seen this before, but well, okay. So once again, remember we had trail and we had values, and this implication graph represented by the levels and by the values. What else do we have? Well, we have the clauses, and I was a little bit like sort of imprecise there. So let's see. So the first simplest way of thinking about this. So right, so we have now let's say literal like 17, and maybe here is like I'm using now Dimex again, not the sort of the unsigned version. And then you have here a container, like which is a list of clauses in which these variables occur. And of course, one way of doing that would be, and that's for instance something I did like in my SATs in my QBF. So the quantor is, well, if you have, yeah, so here 17 occurs, and maybe there's some other literals like -2. Okay, and then well, here's maybe the next clause with 17, maybe a binary clause this time. I guess you get the idea. So you need like additional fields, and maybe if you at the end you put a 0 here. Okay, and then of course, like these would come from somewhere else, right? Like from the and maybe this one also, right? So this is like for full occurrence lists, and their places. Full occurrences means like you need to watch all occurrences of literals in clauses, and that's for certain algorithms important, like for like preprocessing, and but I don't talk about preprocessing today, and but it's really costly. So let's think about it. So this thing here is of course like 4 byte, right? And but what about here this pointer? Okay. Well, this is usually on a today's machine 8 byte, and maybe maybe I should put this in a different colors. Actually, you want to have doubly linked list, like in our variable move to front thing. So this would be another 8 byte. Okay, so that means like for every literal, you not only have kind of the pay load, which is 4 byte, but you have 16 bytes, which gives you a factor 5, right? That's pretty bad. So maybe we forget about this doubly linked list, and that's of course like also possible. But then you need to employ again some garbage collection scheme, and you're still like a factor 3. So this is 3x, right? Because you go from 4 to 12 before you go from 4 to 6 to 20, right? So like 3x versus 5x, then you would again think, oh, is this really that bad? Okay, so this is why this scheme here is rarely used. But before I completely forget about that, let me show you a scheme which in the old days, in the old days was used, and this is where the name comes from. It only watches 2 literals, okay. And this was the observation in the Jeff paper back then in 2001, I think, where they figured, okay, you only need to watch two clauses, and there are like two implementations for that one. The one I'm showing here is kind of the one which was originally done, but which was not in Lindau's version of the code, right? And therefore it got sort of lost. So I got hold of recently of some old version of this code, but it's hard to compile on today's machine. So don't know whether I can still resurrect that code. But anyhow, I independently kind of sorry, this was of course wrong. This last arrow, the same in picosat. So what you see here is kind of the picosat version and the Jeff version for Moskowitz Jeff, not for Lindau's Jeff. All right, so first you would need to understand this watch literal to appreciate it, but maybe it's a good point to explain this here. So what was the really insight, one of the most important insight in that paper was that and there's some predecessor work for Salo actually, that if you have a long clause, like think of this as 10k long, right, then it's really expensive to have all these occurrences, and what actually what you propose, I forgot to you don't have these fields here, so you have a constant size. Only the first two have this watch field, so this was imprecise from me. But you can have like a clause of length 2000, and then you only pay the price here initially. Yeah, this would be 16 byte per clause, right? And now, why is this enough? Well, they have this invariant that you watch two literals in the clause, and they're like they have to be both unassigned. This is the invariant, or a clause contains satisfied literal. And there's like some smaller catch here, so you want to make sure that when you backtrack among this, and this one has to be level of this literal is smaller equal than watched literal level. Okay, so this if you maintain these two invariances somehow through propagation, then you're you make sure that you never miss propagation. In more important, you never miss a clause which is actually unsatisfied, but you didn't find it, right? So if you're not careful, you might watch things which are, you might stop watching a clause or not propagating a clause which is unsatisfiable. And then remember in our discussion, we said like as soon as the number of variables goes, unassigned variables goes to 0, we'll return and say that the formula is satisfiable. If you're not careful here, you would actually claim the formula to be unsatisfiable, while sort of there's still this clause which you cannot reach, which is unsatisfiable, or which you've kind of overlooked. Okay, with these two arguments and then fixing that during propagation, you're getting like almost the state of the art. But this is like around 2001 and 2006 or so. Okay. In the MJEF, like in the ZJEF, which was kind of the first published source code, or at least like the source code which became available, which was at least I saw. I didn't see the MJEF code for a long time. It was slightly different. So there, what did I have here? Maybe 5? No, sorry. What was 5, right? This arrow here is actually wrong. So we're not watching the clause head, so it points to the wrong direction. Actually, we're precisely watching this literal, like as a pointer, right? The pointer address, and then maybe really here the pointer address of when you go through 3, and then because you're not really watching the clause, you don't know where the clause ends, and then they put here like sentinels, maybe 0, so that you know the clause end and the clause beginning, and you need like additional sort of bits here for those literals which are watched, right? And like this one will of course not be watched. Yeah, so you see this is pretty like cumbersome, and you still need like you don't need these guys, of course, these pointers anymore, but you need these additional bits, and maybe you can do stuff them into the rest of the literal, so you can get away with 4 bytes per literal in the clause. The sentinels, of course, like they are cheap. So this was Z-Chef, Lintao Cheng's version. Okay, now we saw already picosat and mchef. There was one catch though in that one, which now I erased, but I have to redo it, because you're only keeping here the sort of the first 2 connected. Okay, and the rest of the literals, like let's see, there's like maybe 4, they don't have any link fields. And now you see 17 could be here, or it could be in the other field. And then you would need to say, okay, so this pointer belongs to 17, while if there's like 13 here, then this pointer belongs to 13. It's still singly list, so a singly list linked, singly list list, and therefore you still need some sort of garbage collection maybe. Anyhow, what if this guy violates now our watch property, right? So it could be that 17 is actually assigned to 0. Now, what we do here is, and this is then later also done in other solvers, we remove the 17 and place it in another, because maybe this guy here is also assigned to 0 here, and this is remains 0. But here there was like maybe a -5, which was actually unassigned. Okay, so you would not need to do this check if this guy is 1. This is like, this would not violate the property, but it's tricky, and yeah, that's another story. So anyhow, so we swapped these 2 guys, right? And this has the strange effect that the clauses are not, the literals in the clause are not like immutable. They kind of change during propagation. Right, and this is again, this is mchef and picosat, and but this is not the best scheme. So around that time already, people came up with the following observation. What if, yeah, this is fine, but what if here now you have a clause which has only 2 literals, like maybe -19 and again 17? Well, then you have again pointers here, right? And yeah, so these pointers, of course, now can point to the start of the clause, because we know that the pointer is for one of the 2 literals. You know from where you come, right? You start propagating from the 17 here, and the right, and then you go to this clause, and then you see, oh, I need to go here because this is the 17. Then I see which okay, I need to go this pointer, right? I guess you get the point. So you need to follow these things, but here it's pretty bad, because you're You're wasting a lot of memory, and in particular, because we discussed this already, there are like lots of cache over usage here. So for this binary clause, we're having really like an overhead. And then, of course, as you probably see, one pointer access, one pointer access, one pointer access. Like for every clause, you have an additional pointer access. And this is and the chunks you need to get in there are bigger. So that is why already partially in Z-Chef, but then later in Minisat, the following scheme became state of the art. Instead of having here directly linked lists, right? You would actually have a stack here. So the stack would contain usually a power of 2 number of entries, and the stack has a begin and end, and then sort of like these guys are invalid, right? And then you really point directly to the clause, and there's like no so maybe 17 minus what did we have, 13, and this guy was the other guy, the longer one, which I of course don't remember anymore what the literal was, right? But you get the point, right? So the advantage here is that this thing here, you only need to load it once, so this gives you one cache miss, and this will be fast, so no overhead, and you shrink the size of this clause memory. Okay, but there's more you can do, and this goes back to Stuckey and Chu, and this is called a blocking literal. And oops, I should have kept that one. Okay, so they observed that, or this also actually was observed in other solvers, and so I remember also writing about that, is that often the other watched literal, so this is the other watched literal, sorry, I should write it below, so the other watched literal, when I traverse this clause starting from 17, right? Then this minus 13 is the other watched literal, and that is in practice very often true, actually. So I think, like in my Picosat paper, I said 60%, but still true probably today. So at least this non-significant part of this if these accesses are completely useless. Why is it useless? Well, I do this pointer dereference here, right? This one here. And then I get this clause memory here into the cache, and then I figure out with 60% probability, oh well, I don't need to look at that clause because the other literal is actually true. And moreover, it's often the other watched literal, even in long clauses, like we had this long clause here before, which where the other watched literal was maybe -5 or so. And also that one is included in this matrix. So one, of course, like needs to redo this experiment. Okay, so you visit these clauses without any use, and that's bad. So instead of doing that, the basic idea here is to increase the size of the stack, which you anyhow have to kind of access at least one, right? And extend it to include here a blocking literal, right? So in this case, it would be just, let's say, -13. For binary clause, right? Here for the long clause, we had like a -5, right? But, and we'll see this later, this is not necessary. It could be any clause, any literal actually could be here, or 7. So it might be -5, but it could also be this 7 here. So I put the 7 here. So it just has to be not the other watched, it should just be one of the literals in the clause. And the reason we cannot really enforce that it's the other watch is because otherwise this would require string propagation to update the other sort of the other watch when we traverse a clause say for 17, and then we swap 17 for some reason, but then yeah, 17 is not the other watch of 5 anymore, so we would need to go the watch list of 5 and update the watches here, but it's not necessary, so we can here have 5 and 7. And now of course what we do is actually, before we make this memory dereference, so this is like a dollar I said, then we're just checking here, and this is also just dollar, whether this 13 is actually true, or like maybe this 7, right? And if this is true, we know it was assigned before 17, or at least at the same decision level. Actually, that's the important part. And therefore, I can just not visit that clause completely, sort of avoid this dollar if, for instance, 7 and minus 13 are both true. All right, so this is a blocking literal and goes back to Chu and Stucky. Blocking literal. But there's more to it. But this more to it was also invented earlier, actually, where people said, okay, so these binary clauses occur so often. Actually, in the SAT competition last year, there were instances with 100 millions of clauses and only 60,000 non-binary clauses. Okay, and then it turns out, if you really look carefully at this, that you don't even need here this whole clause anymore, because also, like, if there's like 13 somewhere, right, then minus 13 would also have here a stack with 17 in it and a pointer to that clause, right? So in essence, the clause is completely represented by these two entries in the watch list. Okay, so that's why we can really remove the whole clause. It's not as easy as you think, because you're well, in this analysis function you saw before in Satch, there was just one loop which went over one reason clause. If you now have sort of like two different kind of reasons, it's engineering wise a little bit tricky. So there are like two types of reasons, binary clauses, where you don't really have the clause, where you only know, okay, it was derived by a binary clause, and there are these long ones, and yeah, you need to distinguish. So this makes the code more tricky. Furthermore, and now it becomes really sort of very interesting in claiming KISAT, I reached sort of the absolute limit. I thought like I had it with Lingeling, but it's not true. So this guy here, this minus 13, right, occupies now, if you think about, and it's actually also true for, so this thing is actually 16 byte wide in Satch. And why? Because the Satzel we were looking, well, because this thing here is 8 byte pointers, and you need to keep things here aligned in a struct. And then actually we put here actually also the size, which is kind of redundant, but we put it there. And okay, so why can't we just kind of shrink the whole thing and just have sort of steal a bit from the literal field and mark it as sort of binary, and then only use like a 4 byte for this guy. So a binary clause would then have four bytes here, and right, this goes away, 4 bytes here. Of course, now the problem is that your the table here on top would have this shape, right? So because for the long clause you still need a reference, and it's clear we cannot afford 8 byte again, because then the whole thing becomes strange. So you would want to have here a 4-byte index of that, which then again limits the number of clauses you can access. But then you really get to the absolute minimum. So this is 4-byte, this is 4-byte, this is 4-byte, and then you have this mixed. So you have then a mixed watch stack list of binary like 4-byte small sort of watches. And then for the large clauses, you have the blocking literal plus a bit that this is a large clause, and the 8-byte. There's like another. And that's why I put here like space for another dot here. Another issue here. Well, there's one bit you need for the whether it's binary or not. But then in addition, right, it's unclear whether this clause is irredundant or not, right? And so if you have the clause in memory, as we also saw like in Sag, you could just have a bit there for denoting this clause is irredundant or is redundant. I mean, for garbage collection, it's not really, like for reduction, it's not really an issue because you keep these binary clauses anyhow. But for like variable elimination for preprocessing algorithm, which really need to know whether the clause is redundant or not, this is not feasible. So you really need to sort of put here another bit here into the this is for the binary, and this here is for a redundant bit, whether the like this watch corresponds to a redundant clause or not, even though the clause is actually not there. But with this, you greatly reduce, of course, the memory usage of the SAT solver by roughly factor 4 to 8. And this way really handle big instances. What do you gain? Well, our current machines get to the limit that you reach with this scheme. So as I said, like KeySat can handle 256 million, like 2 to the power like 28 variables, and after that it just gives up. Also, like this 4-byte offset, of course, is this restriction. So this gives you like 16 gigabyte if you take 8-byte aligned 8-byte aligned clauses in an arena where you take the offset and things like that. So anyhow, so what I figured in practice is like that with this scheme, you're getting up to sort of instances which only run in 128 gigabyte. But if you have machines with 256 gigabyte memory or 512, then you might really sort of jump across this sort of barrier and increase everything by a factor of 2. But then the bad thing is, of course, that you suddenly need twice as much memory, right? So as soon as you have a machine which affords which gets like KeySat to the limits, with say 256 gigabyte of main memory, then another solver which would not use this sort of compact scheme and like just 1 or 2 bits more would require already twice the memory footprint, and you would need to buy a machine with let's say half a terabyte. Okay, now I would suggest we'll look at the code, and for that I have here pre-run Sag, which also shows off one feature here of Sag. Sag has this possibility to completely disable features like blocking clauses. So if you take the option no block, then you're disabling that, and you get like for this slightly more harder factoring example we already looked at before, you get an estimate like how much you gain just by these blocking literals, and as I said, right, it depends like how you count, right? If you start off with the faster version, then going from here to here gives you 50% slowdown, while from here to here is of course like only like 3%. But still it's like a considerable, and if you add a couple of these things together, you can easily make a big improvement. Okay, so maybe I show this non-blocking, this no block first. So you just need to put this environment, this preprocessor variable, and then you get that. But then if you search for this N block, right, disable blocking literals slow down propagation, and there's some more. So you can completely remove restarts, reduction. You can also combine them. Actually, maybe I should show this too. There's like a combinatorial testing script, which of course failed because I just changed something. But in principle, it would reset hard with 2. Oh, there was an error. I'm not sure why this happened. Okay. Anyhow, so we're going to this combinatorial testing should in principle work. So maybe I didn't check it on this latest version, and then this was the point. All these options here, even so you can switch off learning completely. This is the worst thing. For that, I really had to hack actually the script, the regression script to disallow harder benchmarks, because without learning, everything would break down. Then I didn't talk about loss minimization today in this video, so this needs to wait. And then this sorting here, this would disable sorting of the bumped literals. And so you see, you can switch off also this mode switching with the stable and focused, and see like what the software behaves. But there's no blocking here. Now really shows you what this blocking idea is about. Like this is our reference to our class. And then we'll add like these 2 more things, and in principle you only need like a bit here which says the clause is binary or not, but because we have like wasted this 4 bytes anyhow, right? And we need like for the blocking literal the full 32-bit, unless we'll be going down with number of variables. We can as well just to put the whole size there, because these 2 guys would have on a 64-bit machine each 4 bytes, so the whole thing like 8 byte plus this 8 bytes again on a 64-bit machine as found pointer to the class. Then we'll have here the stack, which oh, what was that? The stack, which for the watches with a begin, end, and allocated as usual, and then the actual watches here are just a big array, like the reasons here we looked at before, and also the mark flags, right? And yeah, I didn't talk about phase saving. This is also about this target phases, which also needs to go into another talk. All right, so these watches are then just like an array of stacks, and each each area has here the begin and the end. So maybe go back to the drawing that you see again. So each of these guys would have a begin pointer and an end and an allocated pointer, and maybe I'll just do them in red so that you see what I mean. So this guy here has a begin end pointer, and then of course an end pointer which points to the sort of valid part, and the allocated is here. You need that for kind of like linear accumulated reallocation effort. Okay, that's very basic, and then this is the code which puts a watch into a literal, and it's actually only complicated because of this if-def here, which distinguishes the cases where you have blocking literals and which not, right? If you don't have any blocking literal, then nothing has to be done. This parameter here with the blocking is useless. Otherwise, you put the size there of the clause and the blocking literal, right? And now comes the sort of important part. Watch the 2 first literals in the clause, right? So you take just the 2 first literals and you put them there. This also means there are really no clauses which are unit, and there are no clauses which are empty, right? So they're kind of done by global flags. The empty clause is an inconsistent flag, and the unit clauses are just like global root assignment. Okay, then you watch like exchange wise. Well, lit 0 is the literal for the locally for lit 1, and lit 1 is the one for literal 0. I guess you get the point. So this is actually not the complicated part about watches. You just do this for all classes. The real of course meat of all this is in the propagate literal function. And but before I show that, let me first show you the propagate completely. So the propagate Boolean, call it Boolean constraint propagation. This just gets to the trail, right, and then has here a pointer actually to the literals which have already been propagated, and then all literals to the right on the trail stack need to still pre-propagate it. And that's what we're doing here in this loop, unless there is a conflict, okay? And then we get from the trail at this position, this propagate position, we get the literal which needs to be propagated and propagated until we find the conflict. And the real complicated and one sort of the most important and hotspot function here is this one, propagate literal. And yeah, I don't have time to go over all in details, but I want to go briefly over it because it has maybe some interesting aspects you're not aware of. So first of all, something which also pioneered in KeySat last year is related to what I already said. For this mode switching, you might to watch really compute the time taken in this propagate, right? Propagate is the hotspot, and because it's the hotspot, you can take the effort in that hotspot and use it as a kind of virtual time to make things deterministic. And in the simplest way to do this is computing memory accesses. So that's also what Don Knuth does in his books. He doesn't compute sort of the running time of his algorithm. He uses gigamems, like the number of billion memory operations. However, I found this slightly inaccurate for our users here, because many memory accesses, in particular in the same cache line, and we're optimizing for that even, do not cost much. So what you really want to do is you want to measure these kind of random non-cache memory accesses. And here is like what I found, which seems to work reasonably. The reason why I think it works reasonably, if I look at the running the amount of time spent in blocked and switched search during the focused and stable search. If this mode switching is enabled, which is controlled by this ticks, then you really see that it's like almost 50-50. Of course, it's not like completely, like maybe 40 or something, but it's very close, and that's why this is pretty accurate, I claim, at least like in a factor of 2. We'll just take this number of watches, and then we take the assumed watch cache line size, which is 128 on most machines, at least on this Intel machine I'm showing this. You divide it by the size of one watch, right? And that gives you rough estimate for the number of cache lines you're going to visit when you propagate this particular literal. And this one here is this single dollar sign, right? I mentioned before, you need to go through the you need to get at least access the begin pointer of the stack. All right, and then comes the loop, and then you're kind of walking that watch stack, and by default we keep the watch. Something I have not discussed before, but if you kind of propagate and you go into a clause and you figure out, oh, I found a replacement, then of course that literal you started the propagation with is not watching the clause anymore, and then you need to replace it. In this case, you need to drop the watch, right? Because otherwise you would watch this clause multiple times, more than 2 times. Okay, and because this is the default, we just keep it. And now comes the blocking part. So if you have blocking, then you just get out of the watch the blocking literal, you check its value, and if it's larger 0, well, you can just keep the watch in it. You don't need to access the clause no matter what. This is a very fast sort of path here in the solver, which, as we saw, gave sort of 50% speed. Then The other part is then we can get the size. As I said, like it would be enough to say, okay, it's binary not, because if it's binary, then we actually don't need to go to the clause at all, because we like in a binary clause, the other washed literal is clearly the blocking literal. I mean, like I have to make sure that it's true, but yeah. And then you only need to look at the value, and if it's the blocking literal value is 0, we found a conflict, and otherwise you just assign it. Assignment is actually slightly costly, so I put here like $1, and okay, now comes the very expensive part, right? And if blocking is on, then of course the size of the clause is now large clause, non-binary. Otherwise, it's clause. But this is the only difference here between blocking and non-blocking. So now we need to access the clause. The first part is here where we access the literals, and I don't have time to explain that, what's happening here. But here we're really accessing the first time the cache line in which the clause sits, and most likely this cache line is not in the cache. So because the SAT solvers access memory completely randomly, and therefore we pay a tick for that. Okay, now we get this other watch, and because it might be different from the blocking literal, and also check its value. If it's true, we'll also do nothing. So we just remember that actually. So we're updating the blocking literal with that one, because now that one is better because it's like true. And therefore, next time we do this, we might not need to go to pay this tick. All right, now. Yeah, this is some normalization codes I want to discuss, but now we're searching for the replacement. So here's the loop over the literals of the clause, right? And we start, of course, not at the first literal, but at the third one, like literals plus 2, because this is where we try to find the replacement, right? We try to find like 17 swapped with something else. Okay, and so we just walk this this clause, unless this clause is really long, but I don't really check this in addition, then this is really just like already like captured by this one tick. And then if the replacement value here is larger than 0, we do the same trick as before. We can just replace the blocking literal and don't need to actually do the swapping. This is pretty tricky, and to convince yourself that this is true, actually, that you don't need to update the swap. Otherwise, we're at the watch. Otherwise, well, it could be the replacement value is unassigned. So that means we found the literal which is unassigned, and then we put it as a replacement watch. So we dropped the previous watch, that's this one, then swap the two, and now I have to watch it, of course, right? So this is swapping the literal, for which we started the propagation, and this is like watching the replacement. Okay, otherwise, the replacement is false. The replacement value is false. So we walked starting from 3, we walked to the end of the clause, and all the literals are false. Okay, now we check again the value, which was the other watch's value, and if that one is actually like assigned, then it has to be 0 because we checked the true case already above. Then we found the conflict and report the conflict, right? And then the very final situation is that this other value is now unassigned, right? Because the true case was done above, where we replaced the blocking literal, and then here was the conflict, and now the last case is where we really assign this the clause to the we assign this literal, this other literal, like the other watch literal with the clause which has traversed as reason. Okay. Well, we because the Q kind of follows the P, we need to keep also this thing like in case of conflict, where we have an early abort still consistent. Okay, so this is in a certain sense I would claim the most technical part in the current version of the solver, and but it's really sort of needed, and it's like already like a 15-year-old technology, not like brand new, and therefore I wanted to show you this in detail. So this brings us to the end of this tutorial. I hope you enjoyed it, and you will try some of the source code I presented. It's on GitHub, just for you to remember. There's lots of other material out there on SAT solving, also by me. So just gave a tutorial, as I said, at the SAT SMT summer school. There's a video. Also, there's a CPIOR masterclass all on my webpage. There are a lot of tutorial slides from previous years, from summer school, etc. Of course, there's like SAT solvers, like at least a dozen SAT solvers, some of them winning competitions. It's would be my pleasure if you would take some of these and work with them, and also in particular this last one, which I developed for this occasion, which I continue to develop for some more time, which we call SAT, right, for SAT solver from scratch. So have a look, play with it, and I hope you will have as much fun with SAT solving as I did in the past. Thank you very much. Bye.